Present Condition of the Volcanoes of Southern Italy by G.W. Tyrrell. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Messrs. Washington and Day visited Vesuvius, Etna, Volcano, and Stromboli in the summer of 1914 in order to determine the nature and interactions of the magmatic gases and to confirm the presence of water amongst them, as at Kilauea. They have prepared some interesting notes on the phenomena they witnessed in these volcanoes. Bulletin, Geological Society, America, September 1915. Since the Great Eruption of 1906, Vesuvius has been in a condition of repose, the longest repose interval since the beginning of the 18th century. There is, however, considerable fumarolic activity. The hot acid gases emitted from the fumaroles have disintegrated the rocks in their vicinity and are contributing materially to the demolition of the cone. The floor of the crater is slightly domed, covered with ash from which perfect augite crystals may be gathered, and strewn with angular blocks fallen from the sides. Hot vapors, mainly hydrochloric acid gas, sulfur dioxide, and steam, fill the crater with a blue mist. The summit crater of Etna is now in the middle of an ash cone, rising 1,000 feet above a plateau, both of which are thickly covered with fine, dark gray ash, with many small cones. Concentric fissures indicate that the crater is in process of enlargement. Etna is now showing both fumarolic and strombolian phases at intervals, without marked activity. Volcano has been in an almost continual state of fumarolic activity since its last eruption in 1888 and 9. The circular crater is much shallower than formerly and has two well-defined terraces which run almost completely around the circle. The fumarolic activity is intense and has given rise to a great deposition of salts, mainly sulfates of alumina and potash, which are ankle-deep in places. Stromboli is regarded as the type of continuously active but gently eruptive volcanoes, but recent investigation shows that it presents long periods of varied, but for the most part moderate activity, interrupted by relatively brief periods of repose. 5 active vents were seen by Washington and Day. One of these explodes at short irregular intervals like the discharge of a large caliber gun, and red-hot fragments of half-molten rock are ejected to a height of several hundred meters, accompanied by a tall column of brown smoke. Another small vent blows off at intervals of 20 to 40 minutes with a loud, startlingly sudden blast, like the letting off of steam from a gigantic boiler, with the rapid ascent of a tall, narrow column of white smoke, while the edges of the orifice of eruption grow red-hot. At present, there is not much fumarolic activity on Stromboli. End of The Present Condition of the Volcanoes of Southern Italy by G.W. Tyrrell. Knowledge, 1916. The Recent Activity of Lassen Peak, California, by W.H.W. This LibriVox recording is in the public domain. This old volcano at the southern end of the Cascade Range has shown a remarkable revival of activity during the last 2 years. As set forth by Dr. Diller in a paper in Science for May 26, 1916, the volcano first originated in the Eocene period and carried on its activity during the Miocene and Pliocene, but settled down to a state of quietude in Pleistocene in recent times. The mountain has 4 craters, of which the second is responsible for the present cone. The third broke out near the foot some centuries ago, while the fourth is the new one formed first in 1914. This crater is situated inside the second at the summit of the mountain. At first it was quite small, but is now more than 1,000 feet across and occupies more than half the area of the old crater. In 1914, the eruptions were entirely explosive, the products being chiefly rock fragments, some of which were many tons in weight. In May 1915, however, lava rose in the pipe and overflowed at one place through a notch in the rim of the old crater, forming a flow about a mile long. At the same time, a lid of solid lava was formed over the crater. This was lifted some days later, and a hot blast resembling that of Mount Pelée escaped and rushed down the mountain, devastating about 10 square miles of country, large trees up to 3 feet in diameter being uprooted. Since then, not much activity has been observed, and it seems likely that the period of eruptions is drawing to a close. End of the recent activity of Lassen Peak, California. By W. H. W. Knowledge, 1916. New Theories of Volcanism and A. Brun by G. W. Tyrrell. This LibriVox recording is in the public domain. R. A. Daly, Proceedings of the American Academy of Arts and Sciences, Volume 47, No. 3, 1911, pages 45 to 122, bases a paper on the nature of volcanic action on his well-known theory of abyssal injection. He believes that the worldwide granitic terrain underlying the interrupted sedimentary shell is itself underlain by a shell of eruptible basalt, which is the source and heat-bringer of all igneous action. He points to the fact that all the great lava floods of the world are of basalt, and have welled out from great fissures which are supposed to have tapped this basaltic substratum, although it is not supposed that simple openings extend to this depth. Other igneous rocks are believed to be due to the absorption of the underlying acid shell, as abyssal injections of basalt, caused by crustal deformation, work their way upwards by a method known as stoping. This involves the constant wedging away of blocks from the roof of the resulting batholith and their solution in depth. The resulting mixed magmas are called syntectics, and with or without subsequent differentiation are held to give rise to the known variety of igneous rocks. Daly holds that volcanism is a subsidiary effect of abyssal intrusion. He distinguishes 3 phases of volcanic action: fissure eruptions, in which lava rises with great rapidity through relatively thin cracks in the crust; eruptions through local foundering of the roof of a batholithic intrusion; and central eruptions of the common cone and crater type. Fissure eruptions are well known, and beside the recent Iceland examples, there are numerous others belonging to past ages. The Yellowstone Park rhyolite is believed to be an example of the second type of volcanic action. This huge mass of lava, cut by canyons to a depth of 600 meters without revealing its base, lacking horizontal division planes indicating successive flows, is without parallel amongst lava flows. Daly believes that it passes gradually downwards into a batholithic mass of granite, and is due to the foundering of part of the roof of this batholith, whereby the molten rock was solidified under surface conditions. Certain eruptions are supposed to originate in a cupola-like extension of the roof of a batholithic intrusion, where stoping action would be intensified by a concentration of the hot volatile magmatic fluids. On reaching the surface, the cupola would originate a volcanic focus, and a cone would be formed. At this stage, the problem of the continuance of the volcano becomes the problem of the continuance of heat within the funnel. There are 5 conceivable methods whereby heat may be transferred from the magma to the vent. 1. Explosive removal of material from the upper part of the vent, followed by uprise of magma. 2. Simple outflow of magma at the crater lip. 3. Thermal convection in the lava column. 4. Two-phase convection. 5. The uprise of superheated juvenile gas through the lava column. At Kilauea, on the observation of which this theory is partly based, the first and second methods are inoperative. The third is known to be inefficient in heat transfer, but the fourth, a process conceived to be due to the uprise of comparatively light, hot, gas-permeated magma in the lava column, and its return along the margins of the vent as comparatively heavy, cooled, gas-free magma, may bring a considerable quantity of heat to the surface. This process is believed to be the cause of the lava currents in the crater of Kilauea. The fifth method may be efficient as a heat bringer at some vents, but not at Kilauea. A large overlooked source of heat, according to Daly, is that set free by chemical reaction between the constituents of the hot and active magmatic fluids. Many striking figures are given illustrating the great amount of heat evolved by the reactions between the common elements of these fluids. The process outlined above is known as the gas fluxing hypothesis, and is considered analogous to that of a gas blowpipe. Some explosive types, such as the Reese cauldron and Bendazen, are considered due to the contact of hot magmatic material with vadose waters circulating within the rocks. The explosions here are non-volcanic, but there may be all gradations between this type and those, such as the Hawaiian volcanoes, characterized by quiet magmatic extrusion without explosion. In ordinary volcanoes, there are great variations in the proportions of magmatic and vadose fluids involved, and consequently great variety in modes of eruption. With regard to the now much discussed role of steam in volcanic action, Daly says, quote, "Though the rise of hot magma into rocks charged with vadose or connate water does often cause explosion, the steam pressure produced by such volatilized water can no more be regarded as the cause of volcanism than is the boiling of a kettle the cause of the heat in the stove." Unquote. A. Brun. Whilst Daly emphasizes the adventitious nature of the intervention of water in volcanic action, it is to Brun of Geneva that we are indebted for what appears to be the overthrow of the old axiom that paroxysmal eruption is due to the explosive violence of steam. In the Geological Magazine for June and July, Mr. E.B. Bailey of the Geological Survey gives an illuminating review of the new book, Recherches sur l'exhalation volcanique, by this original and courageous worker. One of the most valuable features of Brun's work is the mass of new and exact experimental data he has accumulated in respect to volcanicity. Not only has he measured the temperature constants of many minerals found in lavas, but new work has been done in the methods of collection, extraction, and analysis of the various volcanic gases, both in the field and in the laboratory. Experimental work on the behavior of rocks during heating has resulted in their classification as active or dead. Active rocks, typified by recent lavas, expand and liberate gas at such a rate, when heated, that the molten material fumes over the edge of the crucible like a miniature lava flow. Active acid rocks are more violent than basic, and give rise to veritable explosions. Dead rocks, among which are schist, granite, and gabbro, give off gas during heating, but at a higher temperature melt quietly without much expansion or violence. The temperature at which gas is emitted in active rocks so rapidly as to cause sudden expansion and explosion is called the explosion temperature. The maximum temperature possible at a volcano is fixed by the explosion temperature of its magma. The principal gases liberated at the explosion temperature are chlorine, hydrochloric acid, and oxides of carbon. The solids evolved are chlorides of the alkali metals and ammonium. Sulfur occurs, but is always in small quantity. Such water as is contained in the rock is always given off before the explosion temperature is reached. These constituents, with the exception of carbon monoxide, are the same as those actually emitted at volcanoes. Brun's main thesis is that paroxysmal explosions are anhydrous, and that the aqueous character of fumaroles is due to the contact of volcanic heat with superficial waters. This view is supported by many striking observations. It is shown, for example, that near the crater of Vesuvius the ashes fall quite dry, but are extremely hygroscopic, owing to the presence of chlorides of iron and magnesium. Moreover, the ash which falls is white, whereas if it had been exposed to the action of water vapor at a high temperature, it would redden immediately, owing to its content of ferrous chloride. In the crater itself, such deliquescing salts as ferric chloride, ferrous chloride, magnesium chloride, and aluminum chloride may be collected dry and undecomposed, whilst hot water vapor would immediately reduce them to oxides. Further evidence is adduced from the study of the white clouds which hang over volcanoes. These are generally regarded as water vapor, but Brun shows that they are persistent and insoluble in the atmosphere as they drift away from the volcanic focus, and are therefore composed of solid particles. At Kilauea, Brun took a series of dew point readings in the great white cloud as it drifted across the crater lip. His results show in every case a lower dew point for the air within than for the air outside the cloud. The lower dew point is believed to be caused by the dilution of the air with anhydrous gases carrying hygroscopic solids in suspension. On the contrary, A markedly elevated dew point was obtained at the peripheral fumaroles, as was indeed to be expected. It seems, therefore, that Brun has at least established the anhydricity of volcanic exhalations, and great probability attaches to his view that water is not the agent to which paroxysmal eruptions must be attributed. End of New Theories of Volcanism and A. Brun by G. W. Tyrrell. Knowledge, 1911. The Role of Water in Volcanic Activity by G. W. Tyrrell. This LibriVox recording is in the public domain. The views of Brun, discussed in Knowledge, September 1911, page 352, that volcanic eruptions are essentially anhydrous, receive emphatic refutation in a paper by Day and Shepard on Water and Volcanic Activity, Bulletin of the Geological Society of America, Volume 24, 1913. This work is based on the study of gases collected from the volcano of Kilauea in pursuance of an extended scheme of study promoted by the Geophysical Laboratory of Washington. Much of Brun's argument depends on the observation that dew point readings taken inside the white cloud emitted from the volcano are actually less than those taken in the clear air outside. Day and Shepard show that the cloud is composed of minutely divided particles of sulfur, not crystalline chlorides as supposed by Brun, around which water may condense. Furthermore, the partial oxidation of the sulfur would produce the dioxide and trioxide, both of which are effective drying agents. It is therefore, quote, a matter of grave doubt whether the readings of a dew point hygrometer in an atmosphere containing SO2 and SO3 have any significance whatever in view of the well-known affinity of these compounds for water, unquote. Successful attempts were made by Day and Shepard to collect the volcano gases before they had reached the air. In the first attempt, no less than 300 cubic centimeters of water accumulated in collecting tubes of 10 liters capacity. Although, owing to the method of collection, this does not represent the proportion of water to the total quantity of volatile matter discharged from the volcano, it proves beyond doubt that these gases contain original water. Analyses of the gases collected shows that the Halemaumau crater yields nitrogen, water vapor, carbon dioxide, carbon monoxide, sulfur dioxide, free hydrogen, free sulfur, with chlorine, fluorine, and perhaps ammonia in comparatively insignificant quantity. After the most critical examination, the nitrogen was found to be free from argon and other rare gases. This affords a good proof that the volcano gases were collected before contact with air, and that volcanic nitrogen is not of atmospheric origin. End of The Role of Water in Volcanic Activity by C. W. Tyrrell. Knowledge, 1914. The Volcanoes of Madagascar by G. W. Tyrrell. This LibriVox recording is in the public domain. Professor A. Lacroix, now the only one remaining of the brilliant trio of French petrologists, the other two members of which were Michel Lévy and Fouquet, writes on the volcanoes of the French colonies in the Indian Ocean, especially those of Madagascar, in an address to the Congrès des Sociétés Savantes à Paris, April 1912. Madagascar contains many volcanoes, both ancient and comparatively recent. The island is built up of a mountainous backbone consisting of crystalline schists and granite, rising abruptly out of a sandy plain on the east coast and from under extensive stratified formations on the west. Volcanic rocks abound in the midst of the sedimentary series. The principal center is at Ankaratra, near the center of the island. The lavas of Ankaratra can be followed without interruption for over 100 kilometers from north to south and 50 kilometers from east to west. The total area covered by the volcanic rocks is certainly not less than 4,000 square kilometers. It is believed that these belong to the Tertiary period, but in the absence of intercalated sediments and fossils, it is impossible to date them exactly. Scoria cones and craters, still intact, show that the volcanic activity persisted until a very late period. Volcanism began in the Ankaratra Massif by a deluge of black lavas, feldspathic basalts, which, to judge by the extent of their flows, must have been emitted in a state of great liquidity. These lavas were erupted from a long series of volcanoes aligned in a north-northeast, south-southwest direction. After this outburst, the centers of activity became more localized and differentiated. In the center and south of the massif, mica trachytes were erupted, and in the southwest, alkali trachytes and phonolites. After this extravasation of pale-colored rocks, a series of black nephelonites were erupted, descending in all directions from the high summits of the chain. The phonolitic rocks of the southwest are remarkable for the fine dome topography they present. The same topography is found in a second but smaller massif, that of Itazi, to the northeast of Ankaratra. The phonolite domes or puys are here accompanied by very recent cones of basaltic scoria and rest upon an undulating surface of ancient rocks, thus reproducing the essential features of the chain of puys in Auvergne. Imagine, says Professor Lacroix, the latter transported to the side of one of the Italian lakes with its blue waters and azure sky, and you will have some idea of the marvelous panorama furnished by the Itazi region. If, however, the local color is to be preserved, it would be necessary to people the lake with enormous crocodiles. End of The Volcanoes of Madagascar by G.W. Tyrrell. Knowledge, 1912. Volcanic Domes by W.H.W. This LibriVox recording is in the public domain. In the American Journal of Science for September 1916, S. Powers describes 5 of these domes which have formed in the last few years since the famous dome and spine appeared on Montagne Pelée. 2 of these arose in Japan and 3 on the Bogoslav volcano in the Bering Sea. The latter were all accompanied by the formation of a spine, and 2 of them were destroyed after the interval of a few months by explosions, showing that they contained gas at high pressure. A crater opened in the top of the 3rd, allowing the gas to escape more slowly, so that it still exists. The rise of the domes on the Japanese mountains could be more carefully watched, and exact details are obtainable. One which rose in the crater of the volcano of Tarumae was formed as part of an ordinary eruption. In the year 1909, after an earthquake, ashes and lapilli were ejected from the crater while the lava was rising in the pipe. When the lava came into the crater, a crust was formed, with the result that the uprising material pushed up the crust, so formed, into a dome. In about a fortnight it grew to a height of 440 feet, but later the center settled down, leaving it lower, and with a flat top, in which form it remained, at any rate, till August 1915. The elevation which occurred at the volcano of Usu was of rather a different nature. After several days of almost continuous earthquake shocks, a line of small craters was opened outside the old crater. When these had been active for some days, a block of land about 1 mile long and 1,000 feet wide began to rise, and was finally raised to a maximum height of 310 feet above its original level in the course of 3 months. It afterwards sank 120 feet. No lava came to the surface, but the block must have been pushed up by the intrusion of magma at a lower level. Minor instances of this phenomenon have been noted on the floors of the crater of Kilauea, and there are besides many ancient domes still remaining, such as the Puy d'Auvergne. End of Volcanic Domes by W.H.W. Knowledge, 1916. Quantitative Study of Active Volcanoes by G.W. Tyrrell. This LibriVox recording is in the public domain. The great quantitative geological investigations which we owe to the Geophysical Laboratory of the Carnegie Institute at Washington are now being supplemented by a study of the physics and chemistry of active volcanoes. Yearbook number 11, 1912. The crater of Kilauea in Hawaii is the one selected for this purpose. During the past summer, it was found possible to descend into the crater and collect the volatile ingredients directly from the lava. These gases were collected and sealed in glass tubes without having come into contact with the air at all. and sent to Washington for detailed study. A very important observation is, however, available, and that is that the temperature of the lava in the active basin varies from day to day, and that this variation depends on the quantity of gas emitted. The temperature rises with an increase of gas emission and falls when the volume of gas diminishes. The composition of the smoke cloud above the volcano, which contains much non-gaseous matter, was also studied, and samples of the liquid lava were taken directly from the molten lake. It is hoped to determine the character of the chemical reactions within the gases, between the gases and the liquid lava, and between the gases and the air, arising out of the recent contention of Brun and others that volcanic eruptions are essentially anhydrous. See Knowledge, April 1911, page 352. It is mentioned that from one of the gases collected directly from the boiling lava, no less than half a pint of water was condensed on cooling. End of Quantitative Study of Active Volcanoes by G.W. Terrell. Knowledge, 1913. Ancient Volcanoes in South Africa by R.H.R. This LibriVox recording is in the public domain. It has long been known that there are in Cape Colony and the adjacent territories many interesting relics of volcanoes of ancient date. Some of these are so old that they have been reduced to the general level of the surrounding country and may even form depressed areas, while in others the original form of the mountain is to a certain extent still preserved. In the former category come the well-known pipes of Kimberley in the Premier mine, which are filled with a peculiar rock known as blue ground. In this are found diamonds. The special feature of this sort of breccia is that it is not composed of volcanic rocks in the ordinary sense of the word, but consists chiefly of fragments of the sediments through which the pipe has been drilled, with an admixture of blocks of igneous rock that appear to have been brought up from great depths by the explosion. Other necks, again, contain a plug of the rather rare rock type, melitite basalt. It has been suggested that the blue ground plugs are the result of a very watery kind of eruption taking place at a comparatively low temperature, and perhaps partaking rather of the nature of a mud volcano. Dr. A. W. Rogers has recently described, in the Transactions of the Royal Society of South Africa, another interesting volcanic mountain presenting some novel features. This mountain, called Getzigubib, is situated in what was formerly German Southwest Africa, near the Keetmanshoop Railway, rising to a height of about 5,000 feet above the sea and 1,800 feet above the high plateau on which it stands. It is ring-shaped and shows a very well-marked central depression, which, however, does not seem to be in reality the original crater, but merely a hollow produced by the more rapid weathering of the softer rock of the plug. The original outlines of the volcano were probably destroyed long ago by denudation. The central plug is very large, about 2 miles in diameter, and is filled by a peculiar breccia consisting for the most part of sedimentary material, some of which may have come from the Karoo series. There are likewise abundant fragments of quartz gabbro and of feldspar and augite derived from the gabbro, but there are no specimens of those peculiar igneous rocks, such as eclogite, which are so characteristic of the Kimberley breccias. Around the neck, the strata of the Fish River series show a very well-marked dip towards the center, such as is seen in many other volcanoes, and they are likewise penetrated by 2 or 3 dikes filled with tuff. The breccias and tuffs resemble those filling pipes and fissures at other localities in South Africa, such as Saltpeter Kop, Kobe River, and Granat Kop, and also appear to have close affinities to some of the tuff-filled Carboniferous necks of Scotland. The most noticeable feature is undoubtedly the complete absence of fragments of lava of the ordinary types. The origin of the tuff-filled necks of this kind presents a difficult problem, and several different explanations have been suggested. Some writers have even supposed that they may be due to the impact of gigantic meteorites, which burrowed down far within the crust of the earth, churning up the rocks and causing them to rise as a kind of pasty mass within the hollow thus produced. This explanation was suggested and discarded by G. K. Gilbert in the case of the Coon Butte crater in Arizona, since the difficulties involved were very great. It cannot, however, be rejected as wholly impossible in all instances. Nevertheless, it seems more probable that these breccia pipes originated from a single great volcanic explosion at a considerable depth, which blew out the overlying rocks mingled with steam and gases, ceasing before lava had time to rise to any considerable height in the vent. In any case, it is clear that the last word has not been written on this subject, and further investigation of the remains of old volcanoes in South Africa may be expected to yield results of great interest and importance. End of Ancient Volcanoes in South Africa by R.H.R. Knowledge, 1916. Volcanic Dust and Climatic Changes by William Marriott. This LibriVox recording is in the public domain. Professor W.J. Humphreys of the United States Weather Bureau, in a paper just published in the Bulletin of the Mount Weather Observatory, has dealt with the subject of volcanic dust and other factors in the production of climatic changes and their possible relation to ice ages. Numerous attempts have been made to find a probable cause for the known climatic changes of the distant past, and especially for those profound climate changes that brought about the extensive glaciation that prevailed during the so-called ice ages. But nearly all the older suggestions have been definitely abandoned because they are inadequate to meet the conditions imposed upon them by the results of geological investigations. Professor Humphreys now puts forward the question of volcanic dust in the upper atmosphere as a factor in the production of climatic changes, including possibly even those great changes incident to the advance and retreat to maximum and minimum of glaciation. In his discussion of the subject, he shows, among other things, that volcanic dust in the high atmosphere decreases the intensity of solar radiation in the lower atmosphere, and therefore the average temperature of the Earth. And this effect has been clearly traced back to 1750, or to the time of the earliest reliable records. It may consequently be said that such a relation between volcanic dust in the upper atmosphere and average temperatures of the lower atmosphere always has obtained, and therefore that volcanic dust must have been a factor, possibly a very important one, in the production of many, perhaps all, past climatic changes, and that through it, at least in part, the world is yet to know many another climatic change in an irregular but well-nigh endless series, usually slight, though always important. But occasionally it may be, as in the past, both profound and disastrous. End of Volcanic Dust and Climatic Changes by William Marriott. Knowledge, 1913. A new volcano. The Secretary of the Treasury has received from Captain M.A. Healy of the United States Revenue Cutter Corwin, under the date of Unalaska, May 28th, 2 interesting reports by officers of the Corwin describing a visit to the recently upheaved volcano in Bering Sea at the northern end of Bogoslov Island, in latitude 53 degrees 55 minutes 18 seconds north, longitude 168 degrees 0 minutes 21 seconds west. This volcano, which is in a state of constant and intense activity, was upheaved from the sea in the summer of 1882, but was not seen by any civilized eye until September 27, 1883, when it was discovered by Captain Anderson of the schooner Matthew Turner. A few days later it was also seen by Captain Haig of the steamer Dora, but no landing upon it was made previous to that by the officers of the Corwin last spring. Dr. Yemens describes it as a dull, gray, irregular, cone-shaped hill about 500 feet in height, from the sides and summit of which great volumes of vapor were arising. At a height of about 2/3 the distance from the base to the apex of the cone, there issued a very regular series of large steam jets, which extended in a horizontal direction, completely across the northwestern face of the hill. Around these steam jets were seen upon nearer approach deposits of sulfur of various hues, which at a distance had looked like patches of vegetation. A landing was effected without difficulty upon a narrow sand spit connecting the new volcano with the old island of Bogoslov, and Dr. Yemens and Lieutenant Cantwell undertook the ascent of the smoking cone. It was covered by a layer of ashes formed into a crust by the action of rain, which was not strong enough to sustain a man's weight, and at every step the climbers' feet crushed through it, and they sank knee-deep into a soft, almost impalpable dust which arose in clouds and nearly suffocated them. As the summit was neared, the heat of the ashes became almost unbearable. A thermometer buried in them halfway up the ascent marked 196 degrees, and in a crevice of the ramparts of the crater, quote, "The mercury rapidly expanded and filled the tube when the bulb burst, and shortly afterwards the solder used in attaching the suspension ring to the instrument was fused." Unquote. The temperature was estimated at 500 degrees Fahrenheit. On all sides of the cone were perforations through which the steam escaped with more or less energy, and in some cases at regular intervals like the exhaust of a steam engine. The interior of the crater could not be seen on account of the clouds of smoke and vapor which filled it. Quote, "A curious fact to be noted," Lieutenant Cantwell says, "in regard to this volcano is the entire absence, apparently, of lava and cinder. Nowhere could I find the slightest evidence of either of these characteristics of other volcanoes hitherto examined in the Aleutian Islands." Unquote. Volcanic dust, or ash, however, is thrown out in considerable quantities and carried by the wind to places as distant as Unalaska. After carefully measuring the volcano and photographing it from various points of view, the exploring party returned without accident to the ship. Captain Healy reports his intention to visit the new volcano again on his return from St. Michael's and the Arctic. Kansas City Review of Science and Industry. End of A New Volcano. Knowledge, 1884. An Examination of the Volcanic Ash of Mont Pelée by Albert B. Middleton. This LibriVox recording is in the public domain. The writer recently had handed to him from a most reliable source, the material having been personally collected on the island of Martinique, West Indies, during a voyage, some of the volcanic ash from Mont Pelée, the eruption of which, it will be remembered, utterly wiped out of existence the adjacent town of Saint-Pierre, with its 30,000 inhabitants. Curious to know whether such a deep-seated disturbance as the one in question had resulted in the expulsion of volcanic material of an unusual nature from a lower depth than ordinary, for this problem of the unexplored inner crust is ever with the geologist, the writer thought that a series of investigations upon this ejected matter, produced during one of the most catastrophic convulsions in the history of volcanology, might possibly bring to light some out-of-the-way features of composition, and the results of the research are given below. Of course, in undertaking this, it was fully recognized that the material in question had not been collected in such a manner as would yield a representative sample, namely, by selecting small average portions over as large an area as possible, but it must be borne in mind that the ordinary methods of sampling which obtain in analytical work would in any case have proved inadequate in view of the colossal nature of the outburst, seeing that tons and tons of the impalpable dust were carried into the upper air hundreds of miles away from the scene of the disaster. In this connection, for example, it may be mentioned that dust from Krakatoa was found floating all over the earth for 3 years after the great eruption. From the commencement, it was assumed that the present constitution of the ash might probably vary very considerably from its original composition, as the molten magma is stated by some authorities to be at a temperature of 2,000 degrees Fahrenheit, even at the moment of its expulsion from the crater. And in case there had been an excess of elements in combination, readily volatilizable at low temperatures, then those not existing as silicates or in other forms which would persist even at high temperatures would naturally be gasified, and would, consequently, not be found in a subsequent analysis. To get some preliminary idea as to the relative proportions of the main constituents, various tests were applied. Flame, blowpipe, and qualitative chemical tests, and spectroscopic and microscopic examinations were also called into requisition, the final results being obtained by quantitative chemical analysis. It speedily became evident from the chemical tests that none but the ordinary metals usually found in such materials were present to any extent, a search for such metals as copper, lead, silver, chromium, bismuth, and others being unsuccessful. a slight trace of manganese was noticed, and a quantitative analysis for nickel and barium, which were originally suspected of being present, proved both these latter elements to be absent. For the spectroscopic examination, a portion of the scoria was dissolved in hydrochloric acid and evaporated to dryness in order to separate the silica. On redissolving, the siliceous residue was filtered off, and the resultant chlorides transferred to a Mitscherlich tube, fed therefrom into the flame of a Bunsen burner, and examined through an ordinary direct vision instrument. This revealed the alpha lines of calcium, which element was found by separate analysis to be present as calcium oxide to the extent of some 7%. No other indication of any importance was observed by this method, the non-appearance of the alkalis being probably due to the fact that the insoluble residue in which these are often in combination was filtered off. Another portion of the ash was examined through a petrological microscope in conjunction with a polariscope under about 150 magnifications. This showed that the great bulk of the material was composed of the unindividualized glassy silicates usually observable in such cases, with an occasional crystal here and there, the brilliant appearance of which, under the crossed nickels, indicated them to be quartz. The particles were highly vesicular, some being drawn out into the characteristic tubular form, thus betraying the manner of their origin. No magnetite was noticeable. As commonly found in materials of this nature, the sudden cooling of the magma at the moment of expulsion had prevented anything like a crystalline structure obtaining throughout the mass. A sample of ash from Cotopaxi, collected from Chimborazo, 65 miles distant, by the celebrated mountaineer Whymper, was examined side by side with the above, and presented a very similar appearance, save that the particles were nothing like so vesicular. It appeared increasingly evident, therefore, that the ash was one quite of the ordinary type. The ground having thus been cleared, a quantitative analysis was next undertaken. A portion of the gritty gray dust was triturated, passed through a 90-mesh sieve, and was then ignited in order to normalize it with regard to hygroscopic moisture and to bring it in line with the conditions obtaining at the moment of expulsion. The analysis was proceeded with as in the case of an ordinary acid refractory material until the silica was separated, after which the subsequent processes were dealt with as in an iron ore. The results obtained are given in round figures as under: silica, silicon oxide, SiO2, 57, alumina, aluminum oxide, Al2O7, 21, oxide of iron, ferrous oxide, FeO, 7, lime, calcium oxide, CaO, 7, magnesia, magnesium oxide, MgO, 3, alkalis, X sodium oxide, Na2O, Y potassium oxide, K2O, say 5 to balance. It will be seen from this, therefore, that the ash, far from presenting any features of an extraordinary nature, practically corresponds in composition to an ordinary intermediate igneous rock, the ultimate constitution of a typical sample of which is here given for purposes of comparison. Silica, 60, alumina, 15, alkalis, 6, alkaline earths, 10, oxides of iron and manganese, 9. End of an examination of the volcanic ash of Mont Pelée by Albert B. Middleton. Knowledge, 1909. Volcanology by Alexander Scott. This LibriVox recording is in the public domain. The latest number, Volume 2, Part 3, of the recently instituted Zeitschrift für Volcanologie, which has come to hand, contains several interesting studies on volcanic activity. K. von Komarowitz describes in detail the various types of structures which are found in North Celebes. Sopoten, the chief volcano, resembles the Pico de Teide and consists of two cones in a large depression filled with recent lava. The older cone, which reaches a height of 1,900 meters and has been quiescent for some time, has been formed by the piling up of scoria, lapilli, and ashes, bombs being rare. while the younger cone, which is 1,500 meters high and has been active recently, belongs to the Stromboli type and is composed of loose scoria. The latter cone is not parasitic, but has been formed through the blocking of the pipe of the former by a mass of solidified lava. The lava field resembles those of Iceland, while there are also some small craters belonging to the type prevalent in the latter island. The other types include several surface craters lying on a plateau, a long fissure flanked by ridges of ash, and a crater which has undergone partial erosion and is now in the form of a horseshoe. The products of the recent activity are partly semi-plastic material, resembling the so-called lava blockstrom, and partly crumbling, very vesicular pumice. H. Simotomai reviews the eruptions during the last century of the volcanoes of the Fuji and Kirishima zones in Japan, and gives a description of the cauldron of Kutscharo. The latter depression is about 28 kilometers in diameter, and except for an opening in the southeast side, is surrounded by walls rising to a height of 1,000 meters. It seems to have been formed by the foundering of volcanic agglomerate and contains several fumaroles, from which large amounts of sulfur, 450 tons annually, are obtained. J. F. Tristan gives a note on some recent outbreaks of the Poas volcano in Costa Rica. These consisted mainly of eruptions of mud and steam, the activity resembling that of an immense geyser. The characteristic forms which the ejected mud assumes are shown in some very fine photographs. The most noteworthy consists of a mass of radiating pillars, nearly vertical, and rising to a height of 175 meters. End of Volcanology by Alexander Scott. Knowledge, 1916. Earthquake Regions by Richard A. Proctor. This LibriVox recording is in the public domain. Earthquakes occur in all regions adjacent to active volcanoes. Thus, the neighborhood of Vesuvius, Etna, and Tenerife is infested by subterranean convulsions, which also are frequent over the neighborhood of the Greek archipelago and in Syria. In fact, it seems probable that the whole of the Mediterranean basin and the surrounding lands for a distance of many miles from its shores form a single earthquake district, whereof Tenerife, Vesuvius, Etna, Stromboli, the archipelagic, and the Syrian volcanoes are the safety valves. Then there is another earthquake region surrounding Hekla, or some say, extending in a long line from the Jan Mayen volcano through Hekla, the Azores, and the Cape Verde Islands to St. Helena and Tristan da Cunha. Japan, Sumatra, Java, and the islands of the East Indian archipelago are liable to fearful earthquakes, some of the most destructive of which have occurred within the last few years. In the West Indies there is another earthquake region, to which must be referred those which have recently taken place. Probably this district belongs to the great earthquake region in Colombia and Peru, around the celebrated volcanoes Cotopaxi and Chimborazo. The southwestern district of the United States is also liable to earthquake shocks, apparently referable to the great Mexican volcanoes. There is one region of the earth in which subterranean shocks occur which cannot be referred to the neighborhood of volcanic vents. Upper India and parts of western India are liable to frequent earthquakes, insomuch that between the years 1800 and 1842, no less than 162 earthquakes were recorded in these places. Undoubtedly, we may trace these disturbances to the great mountain chains which traverse this part of Asia. The subterranean forces which upheaved the great Himalayan range, for instance, may be assumed to be still existent, though now for a while dormant, or perhaps, says Sir John Herschel, expended in maintaining the Himalayas at their present elevation. On the other hand, there are some regions wholly free from earthquake shocks. Among such may be mentioned the great alluvial plains of America east of the Andes, the plains of the northeast of Europe, and the northern parts of Asia. There are monuments, natural and artificial, which prove the absolute fixity of some regions. The slightest shock would have flung down that strange mass which is perched upon the summit of the Peter Botte Mountain, 1,500 feet above the sea level. Pompey's pillar justifies the assertion of Strabo that Egypt has long been free from earthquakes, though nothing short of subterranean convulsion could have flung down the more ancient obelisks which lie prostrate amidst the sands of western Lower Egypt. Even that masterpiece of Egyptian labor, the Great Pyramid, though surpassing all other human erections in stability, shows unmistakable evidence of the slow action of subterranean forces. The quantity of the post-pyramid tilt, says Professor Piazzi Smythe, appears to be about 37 seconds, as given by the corner angles of the Great Pyramid. In Mexico, again, in the very center, seemingly, of earth-rocking forces, there is a region in which rocks of grotesque figure attest the perfect immunity which the region has enjoyed even from inconsiderable shocks. The Cheese Ring in Devonshire is another instance of the kind of evidence we are considering. And as there are no instances of regions near to a disturbed district which yet are free from shocks, so there are spots liable to frequent shocks, though the neighboring country for miles on every side is seldom, if ever, disturbed. Such is the district, very limited in extent, near Comrie in Perth, where a year scarcely ever passes without a shock being experienced. It would seem also as if regions free from subterranean disturbance for many centuries must not count upon permanent immunity, for a violent earthquake will often open out, as it were, a passage for subterranean impulses to new regions. The circles of concussion enlarge, says Humboldt, in consequence of a single extremely violent shock. Since Cumana was destroyed, December 14, 1797, every shock of the southern coast is felt in the peninsula of Managuares, which before suffered no disturbance. Again, in the successive earthquakes which traversed, in 1811 through 13, the valley of the Mississippi, Arkansas, and Ohio rivers, it was noteworthy how the motion traveled farther and farther northward on each occasion. It seemed as if the subterranean forces were gradually breaking away through successive barriers. End of Earthquake Regions by Richard A. Proctor. Etna's Eruptions, Part 1. This LibriVox recording is in the public domain. There is a marked contrast between the circumstances of the eruptions of Etna which have taken place this year and in the summer of 1879, and those of the Great Eruption of 1868. For before the two last eruptions, the great South European volcanic system had shown but few signs of disturbance, and those only slight. But when in November 1868 Etna burst into eruption, the volcanic system of southern Europe had been disturbed during 13 months by subterranean movements. Scarcely a single portion of the wide area included under that name had been free from occasional shocks of earthquake. There had been shocks at Constantinople, at Bucharest, at Malta, and at Gibraltar. Mount Vesuvius, the most active, though not in all respects the most important of the outlets by which that system finds relief, had been in a state of activity during the whole of the preceding year, and several times in actual eruption. But it had seemed as though Vesuvius, owing perhaps to changes which had taken place in its subterranean ducts and conduits, had been unable to give complete relief to the forces then at work beneath the southern parts of Europe. Whenever Vesuvius had been quiescent for a while during 1868, earthquakes occurring at far distant places not only showed the connection which exists between the action of Vesuvius and the condition of regions far remote from Vesuvius, but that great Neapolitan outlet was not able to relieve as usual the remote parts of that wide volcanic region. Even in England and Ireland there were earthquakes, at times corresponding significantly with the temporary quiescence of Vesuvius. In fact, scarcely 10 days had passed after the occurrence of an earthquake which alarmed the inhabitants of Western Europe before a great eruption of Vesuvius began. A vast cone was thrown up, from which the imprisoned fires burst forth in rivers of molten lava, and round the base of this cone other smaller ones formed themselves, which added their efforts to that of the central crater, and wrought more mischief than in any eruption of Vesuvius since that of 1797. But, enormous as was the quantity of lava which those cones poured forth, it would seem that Vesuvius was still unable to give perfect relief to the imprisoned gases and fluids which had long disturbed the south of Europe. All that Vesuvius could do had been done. The smaller cones had discharged the lava which communicated directly with them, and had then sunk to rest. The great cone alone continued, but with diminished energy, to pour forth masses of burning rock and streams of liquid lava. That the imprisoned subterranean fires had not fully found relief was shown by the occurrence of an earthquake at Bucharest late on the evening of November 27th, which was only a day after the partial cessation of the eruption of Vesuvius. Probably the masses of liquid fire which had been flowing towards Vesuvius had collected beneath the whole of that wide district which underlies Etna, Stromboli, and the Neapolitan vents. Be this as it may, it is certain that but a few hours after the occurrence of the earthquake in Wallachia, Mount Etna began to show signs of activity, and by the evening of November 28, 1868, was in violent eruption. When we consider these circumstances in connection with the recognized fact that Etna is an outlet of the same volcanic system, we can hardly be surprised that the ineffectual efforts of Vesuvius should have been followed by an eruption of the great Sicilian volcano. We can imagine that the lakes of fire which underlie the Neapolitan vent should have been inundated, so to speak, by the continual inrush of fresh matter, and that thus an overflow should have taken place into the vast caverns beneath the dome of Etna, which had been partially cleared when the Sicilian mountain was in eruption in 1865. During a whole year some such process had probably been going on, until at length the forces which had been silently gathering themselves were able to overcome the resistance of the matter which stopped up the outlets of Etna, and the mountain was forced into violent and remarkably sudden action. Unlike Vesuvius, Etna has always, within historic times, been recognized as an active volcano. Diodorus Siculus speaks of an eruption which took place before the Trojan War and was so terrible in character as to drive away the Sasani who had peopled a neighboring district. We learn also from Thucydides that in the 6th year of the Peloponnesian War, a lava stream destroyed the suburbs of Catania. This eruption, says the historian, was the third which had taken place since the island had been colonized by the Greeks. Classical readers will scarcely need to be reminded of Pindar's graphic description of the eruption which took place 50 years before the one referred to by Thucydides. Although the poet only alludes to the mountain in passing, he has yet succeeded in presenting with a few skillful strokes the solemn grandeur of ancient Etna, the scene of the struggles of the buried giant Typhoeus. He portrays the snowy mountain as the pillar of the heavens, the nurse of eternal snows, hiding within deep caverns the fountains of unapproachable fire. By day a column of eddying smoke, by night a bright and ruddy flame, while masses of burning rock roll ever with loud uproar into the sea. The cone of Etna rises to more than twice the height of Mount Vesuvius. Of old, indeed, the Sicilians assigned to their mountain a height not falling far short of that of the great Alpine mountains. But in 1815, Captain, the late Admiral Smythe, ascertained by a careful series of trigonometrical observations that the true height of the mountain is 10,874 feet. The Catanians were indignant that a young and at that time undistinguished Englishman should have ventured to deprive their mountain of nearly 2,000 feet of the height which had been assigned to it by their own observer, Recupero, and they refused to accept the new measurement. 9 years later, however, Sir John Herschel, from barometrical observations, estimated the mountain's height at 10,872.5 feet. The close agreement between the two results was spoken of by Herschel, Lyell tells us, as a happy accident. But as Dr. Wollaston remarked, it was one of those accidents which would not have happened to two fools. The figure of Etna is a somewhat flattened cone, which would be very symmetrical were it not that on the eastern side it is broken by a deep valley called the Val des Beauvais, which runs nearly to the summit of the mountain, and descending halfway down its banks is connected with a second and narrower valley called the Val di Colonna. The cone is divided into 3 regions called the desert, the woody, and the fertile regions. The first of these is a waste of lava and scoriae, from the center of which uprise the great cone. The woody region encircles the desert land to a width of 6 or 7 miles. Over this region, oaks, pines, and chestnut trees grow luxuriantly, while here and there are to be seen groves of cork and beech. Surrounding the woody region is a delightful and well-cultivated country, lying upon the outskirts of the mountain and forming the fertile region. This part of Etna is well inhabited, and thickly covered with olives, vines, and fruit trees. One of the most singular peculiarities of the mountain is the prevalence over its flanks of a multitude of minor cones, nearly 100 of which are to be seen in various parts of the woody and fertile regions. Of these, Sir Charles Lyell remarks that, although they appear but trifling irregularities when viewed from a distance as subordinate parts of so imposing and colossal a mountain, they would, nevertheless, be deemed hills of considerable magnitude in almost any other region. It has been calculated that the circumference of the cone is fully 87 English miles, but that the whole district over which the lava extends has nearly twice that circuit. Of the earlier eruptions of Mount Etna, we have not received very full or satisfactory records. It is related that in 1537 the principal cone, which had been 320 feet high, was swallowed up within the hollow depths of the mountain. And again, in 1693, during the course of an earthquake which shook the whole of Sicily and destroyed no fewer than 60,000 persons, the mountain lost a large portion of its height, insomuch that, according to Boccone, it could not be seen from several parts of the Valdemone, whence it had before been clearly visible. Minor cones upon the flanks of the mountain were diminished in height during other outbursts in a different manner. Thus, in the great eruption of 1444, Monte Peluso was reduced to 2/3 of its former height by a vast lava stream which encircled it on every side. Yet, though another current has recently taken the same course, the height of this minor mountain is still 300 or 400 feet. There is also, says Sir Charles Lyell, a cone called Monte Nucila near Nicolosi, round the base of which successive currents have flowed, and showers of ashes have fallen since the time of history, till at last, during an eruption in 1536, the surrounding plain was so raised that the top of the cone alone was left projecting above the general level. But the first eruption of which we have complete and authentic records is the one which occurred in the year 1669. An earthquake had taken place by which Nicolosi, a town situated about 20 miles from the summit of Etna, was leveled to the ground. Near the site of the destroyed town, 2 gulfs opened soon after, and from these gulfs such enormous quantities of sand and scoriae were thrown out that a mountain having a double peak was formed in less than 4 months. But remarkable as was the evidence thus afforded of the energy of the volcanic action which was at work beneath the flames of the mountain, a yet more striking event presently attracted the attention of the alarmed inhabitants of the neighboring country. On a sudden, and with a crash which resounded for miles around, a fissure 12 miles in length opened along the flanks of the disturbed mountain. The fissure extended nearly to the summit of Etna. It was very deep, how deep is unknown, but only 6 feet in width. Along its whole length there was emitted a most vivid light. Then, after a brief interval, 5 similar fissures opened one after another, emitting enormous volumes of smoke, and giving vent to bellowing sounds which could be heard at a distance of more than 40 miles. At length the eruption commenced in earnest. The volume of lava which was poured forth was greater than any that has ever been known to flow from the mountain during historical times. According to the estimate of Ferrara, no less than 140 millions of cubic yards of lava were poured down the sides of the mountain. The current, after melting down the foundations of a hill called Montpellier, overflowed no fewer than 14 towns and villages, some of which had as many as 3,000 and 4,000 inhabitants. Alarmed at the progress of the sea of lava which threatened to overwhelm their city, the Catanians upreared a rampart of enormous strength and 60 feet in height. So stoutly was this bulwark established that the lava was unable to break it or to burn it down. The molten sea gradually accumulated until at length it rose above the summit of the rampart, from which it poured in a fiery cascade and destroyed the nearer part of the city. The wall was not thrown down, however, says Charles Lyell, but was discovered long afterwards by excavations made in the rock by the Prince of Biscari, so that the traveler may now see the solid lava curling over the top of the rampart as if still in the very act of falling. The current had performed a course of 15 miles before it entered the sea, where it was still 600 yards broad and 40 feet deep. It covered some territories in the environs of Catania, which had never before been visited by the lavas of Etna. While moving on, its surface was in general a mass of solid rock, and its mode of advancing, as is usual with lava streams, was by the occasional fissuring of the solid walls. A gentleman of Catania, named Pappalardo, desiring to secure the city from the approach of the threatening torrent, went out with a party of 50 men whom he had dressed in skins to protect them from the heat, and armed with iron crows and hooks. They broke open one of the solid walls which flanked the current near Belpasso, and immediately forth issued a rivulet of melted matter which took the direction of Paterno. But the inhabitants of that town, being alarmed for their safety, took up arms and put a stop to further operations. In the eruption of 1755, a singular circumstance occurred. From the Val de Bove, usually dry and arid, there flowed a tremendous volume of water, forming a stream 2 miles broad and in some places 34 feet deep. It flowed in the first part of its course at the rate of 2 miles in 3 minutes. It is said to have been salt, and many supposed it had been in some way drawn from the sea, since its volume exceeded that of all the snow on the mountain. It has, however, since been found that vast reservoirs of snow and ice are accumulated in different parts of the mountain beneath the lava. The snow was melted by the heat of the rising lava and was made salt by vaporous exhalations. Of the singular solidity of the walls of an advancing lava stream, Recupero has related a remarkable instance. During the eruption of 1766, he and his guide had ascended one of those minor cones which lie, as we have said, on the flanks of the mountain. And from the summit of this hill they watched with feelings of awe the slow advance of a fiery river 2.5 miles in breadth. Suddenly they saw a fissure opening in the solid walls which encircled the front of the current of lava, and then from out this fissure 2 streams of lava leaped forth and ran rapidly towards the hill on which the observers were standing. They had just time to make their escape, when turning round they saw the hill surrounded by the burning lava. 15 minutes later the foundations of the hill had been melted down, and the whole mass floated away upon the lava, with which it presently became completely incorporated. It would be a mistake, however, to suppose that such an occurrence as the one we have just related is often observed. On the contrary, it seems that, when burning lava comes into contact with rocky matter, the latter is usually very little affected. It is only when fresh portions of incandescent lava are successively brought into contact with fusible rocks that these can be completely melted. Sir Charles Lyell quotes a remarkable story in illustration of the small effects which are produced by lava when there is not a continual supply of fresh material in an incandescent state. Quote, "On the site of Montpellier, one of the towns overflowed in the great eruption of 1669, an excavation was made in 1704, and by immense labor the workmen reached, at the depth of 35 feet, the gate of the principal church, where there were 3 statues held in high veneration. One of these, together with a bell, some money, and other articles, was extracted in a good state of preservation from beneath a great arch formed by the lava." Unquote. This will seem the more extraordinary when it is remembered that 8 years after the eruption the lava was still so hot at Catania that it was impossible to hold the hand in some of the fissures. Among the most remarkable of the eruptions of Etna which have taken place in recent times are those of 1811 and 1819. In 1811, according to Gemellaro, the great crater gave vent at first to a series of tremendous detonations, from which it was judged that the dome of the mountain had become completely filled with molten lava, which was seeking to escape. At length a violent shock was experienced, and from what followed it would seem that by this shock the whole internal framework of the mountain had been rent open. For first a stream of lava began to pour out from a gap in the cone not far from the summit. Then another stream burst out at an opening directly under the first and at some distance from it. Then a third opening appeared, still lower down, then a fourth, and so on, until no less than 7 openings had been formed in succession, all lying in the same vertical plane. From the way in which these openings appeared, and the peculiarity that each stream of lava had ceased to flow before the next lower one burst forth, it is supposed that the internal framework of the mountain had been rent open gradually from the summit downwards, so as to suffer the internal column of lava to subside to a lower and lower level, by escaping through the successive vents. This, at least, is the opinion which Scrope has expressed on the subject, in his treatise on volcanoes. To be continued. End of Etna's Eruptions, Part 1. Knowledge, 1886. Etna's Eruptions, Part 2. This LibriVox recording is in the public domain. The eruption of 1819 was in some respects even more remarkable than that of 1811. The Val de Bove, which, as already mentioned, breaks in upon the dome of Etna upon the eastern side, was covered by a sea of burning lava. 3 large caverns had opened not far from the fissures, out of which the lava had flowed in 1811, and from these, flames, smoke, red-hot cinders, and sand were flung out with singular impetuosity. Presently another cavern opened lower down, but still no lava flowed from the mountain. At length a 5th opening formed, yet lower, and from this a torrent of lava poured out, which spread over the whole width of the Val de Bove, and flowed no less than 4 miles in the first 2 days. This torrent of lava was soon after enlarged by the accession of enormous streams of burning matter flowing from the 3 caverns which had formed in the first instance. The river of lava at length reached the head of the Colonna Valley, where there is a vast and almost vertical precipice, over which the lava streamed in a cataract of fire. But there was a peculiarity about the falling lava which gave to the scene a strange and awful character. As the burning cascade rushed down, it became hardened through the cooling effects due to its contact with the rocky face of the precipice. Thus the matter which had flowed over the head of the valley like a river of fire fell at the foot of the precipice in the form of solid masses of rock. The crash with which the falling crag struck the bottom of the valley is described as inconceivably awful. At first, indeed, the Catanians feared that a new eruption had burst out in that part of the mountain, since the air was filled with clouds of dust, produced by the abrasion of the face of the precipice as the hardened masses swept over it. The length of time during which the lava of 1819 continued to flow down the slopes of the great valleys is well worth noticing. Mr. Scrope saw the current advancing at the rate of a yard per hour 9 months after the occurrence of the eruption. The mode of its advance was remarkable. As the mass slowly pushed its way onward, the lower portions were arrested by the resistance of the ground, and thus the upper part would first protrude itself, and then, being unsupported, would fall over. The fallen mass would then in its turn be covered by a mass of more liquid lava, which poured over it from above. And thus the current had all the appearance of a large heap of rough and large cinders rolling over and over upon itself by the effect of an extremely slow propulsion from behind. The contraction of the crust as it solidified, and the friction of the scoriform cakes against one another produced a crackling sound. Within the crevices a dull red heat might be seen by night, and vapor issuing in considerable quantity was visible by day. The circumstance that Etna uprears its head high above the limit of perpetual snow has a remarkable bearing on the characteristics of this volcano. The peculiarity is touched on by Pindar in the words already quoted, in which he speaks of Etna as the nurse of everlasting frosts concealing within deep caverns the fountains of unapproachable fire. It will be readily conceived that the action of molten lava upon the enormous masses of snow which lie upon the upper part of the mountain must be calculated to produce, under special circumstances, the most remarkable and, unfortunately, the most disastrous effects. It does not always happen that fire and ice are thus brought into dangerous contact, but records are not wanting of catastrophes produced in this way. In 1755, for example, a tremendous flood was occasioned by the flow of the 2 streams of lava from the highest crater. The whole mountain was at the time, March 2nd, covered with snow, and the torrent of lava formed by the union of the 2 streams was no less than 3 miles in width. The flow of such a mass of molten fire as this over the accumulated snows of the past winter led to most disastrous consequences. A frightful inundation resulted, says Sir Charles Lyell, which devastated the sides of the mountain for 8 miles in length, and afterwards covered the lower flanks of Etna, where they were less steep, together with the plains near the sea, with great deposits of sand, scoriae, and blocks of lava. In connection with this part of the subject may be mentioned the singular and apparently paradoxical circumstance that in 1828 a large mass of ice was found, which had been preserved for many years from melting by the fact that a current of red-hot lava had flowed over it. We might doubt the occurrence of so strange an event, were it not that the fact is vouched for by Sir Charles Lyell, who visited the spot where the ice had been discovered. He thus relates the circumstances of the discovery. The extraordinary heat experienced in the south of Europe during the summer and autumn in 1828 caused the supplies of snow and ice, which had been preserved in the spring of that year for the use of Catania and the adjoining parts of Sicily and the island of Malta, to fail entirely. Great distress was consequently felt for want of a commodity regarded in those countries as one of the necessaries of life rather than an article of luxury, and the abundance of which contributes in some of the larger cities to the salubrity of the water and the general health of the community. The magistrates of Catania applied to Signor Gemellaro in the hope that his local knowledge of Etna might enable him to point out some crevice or natural grotto on the mountain where drift snow was still preserved. Nor were they disappointed, for he had long suspected that a small mass of perennial ice at the foot of the highest cone was part of a large continuous glacier covered by a lava current. Having procured a large body of workmen, he quarried into this ice and proved the superposition of the lava for several hundred yards, so as completely to satisfy himself that nothing but the subsequent flowing of the lava over the ice could account for the position of the glacier. In other words, the ice had not accumulated in a cavern of moderate extent accidentally formed beneath overhanging lava masses. Unfortunately for the geologist, adds Lyell, the ice was so extremely hard and the excavation so expensive that there is no probability of the operations being renewed. This strange phenomenon is explained in all likelihood by the fact that the drift of snow over which the lava flowed had become covered with a layer of volcanic sand before the descent of the molten matter. The effect of sand in resisting the passage of heat is well known. Nasmyth, the inventor of the steam hammer, illustrated this property in a remarkable manner by pouring 8 tons of molten iron into a cauldron 1/4 of an inch thick, lined with a layer of sand and clay, somewhat more than half an inch thick. When the fused metal had been 20 minutes in the cauldron, the outside was still so cool that the palm of the hand could be applied to it without inconvenience, and lava consolidates so quickly that there must soon have been formed over the snow a solid covering, strong enough to resist the effects of the fresh molten matter which was continually streaming over it. In this way we may readily conceive, as Sir Charles Lyell has remarked, that a glacier 10,000 feet above the sea level would endure as long as the snows of Mont Blanc unless heated by volcanic heat from below. It is worthy of notice that in the Antarctic seas there is an island called Deception Island, which is almost entirely composed, according to the authority of Lieutenant Kendall, of alternate layers of ice and volcanic ashes. One of the most perplexing subjects to geologists is the existence of so remarkable a valley as the Val de Bove, breaking the contour of the dome of Etna nearly to the summit. It must be remembered that there are few subjects which have been more carefully examined than the question of the formation of valleys and ravines. The primary agent recognized by geologists is the action of subterranean forces in upheaving and depressing the land. In this way, doubtless, all the principal valleys have been formed. But fluviatile influences have also to be considered, and a valley which exists upon the flank of a mountain may, in nearly every instance, be ascribed to the action of running water. In the case of the Val de Bove, however, we are forced to come to a different conclusion. If this valley had been formed by the action of running water in some long past era of the mountain's history, the chasm would have deepened as it approached the base. On the contrary, the precipices which bound the Val de Bove are loftiest at the upper extremity, and gradually diminish in height as we approach the lower regions of the mountain. Nor can we imagine that the valley has been formed by a landslip. The dimensions of the depression are altogether too great for such an explanation to be available. And passing over this circumstance, we are met by the consideration that, if the land which once filled this valley had slipped, in the ordinary sense of the term, we should see the traces of the movement, and be able to detect the existence of the removed mass. Not only is there no evidence of a motion of this sort, but the slightest examination of the valley at once disposes of the supposition that such a motion can at any time have taken place. It remains only that we suppose the valley to have been caused by the bodily subsidence of the whole mass which had formerly filled up what is now wanting to the dome-shaped figure of the mountain. And the subsidence must have taken place in a sudden manner, not necessarily in a single shock, but certainly not by a slow process of sinking, for the mass which has sunk is sharply separated from the rest, so that the precipitous walls of the valley exhibit the structure of the mountain's frame to a depth of from 3,000 to 4,000 feet below the summit of the cone. In other words, a portion of the crust has been separated from the rest, and has then sunk bodily down, leaving the remainder unchanged. When we consider the dimensions of the valley, such an event becomes very startling. The Val de Beauvais, says Lyell, is a vast amphitheater, 4 or 5 miles in diameter, surrounded by nearly vertical precipices. One might almost be prepared to doubt that such a valley as this could be formed in the manner described, were it not that within recent times we have had evidence of the occurrence of similar events. During a violent earthquake and volcanic eruption which took place in Java in 1822, the face of the mountain Galunggung was totally changed, its summits broken down, and one side, which had been covered with trees, became an enormous gulf in the form of a semicircle. This cavity was about midway between the summit and the plain and surrounded by steep rocks. Yet more remarkable was the great subsidence which took place in the year 1772 on Papandayang, the largest volcano in the island of Java. On that occasion, an extent of ground 15 miles in length and 6 in breadth, covered by no less than 40 villages, was engulfed, and the cone of the mountain lost 4,000 feet of its height. There is nothing unreasonable, therefore, in supposing that some such event may have resulted in the formation of the strange valley which mars the dome-shaped figure of Mount Etna, although no such events have been witnessed in the neighborhood in recent times. One singular feature of the valley remains to be mentioned. The vertical face of the precipices which bound it are broken by what, at a distant view, appear to be dark buttresses, strangely diversified in figure and of tremendous altitude. On a closer inspection, however, these strange objects are seen to be composed of lava jutting out through the face of the cliffs. Being composed of harder materials than the cliffs, they waste away less rapidly, and thus it is that they are seen to stand out like buttresses. Now we would invite the close attention of the reader to this part of our subject, because, as it seems to us, it illustrates in a singularly interesting manner the mode in which volcanic cones are affected during eruption. We have seen that in the eruption of 1811 there was evidence of a perpendicular rent having taken place in the internal framework of Etna, and in 1669 a fissure was formed which extended right through the outer crust. In one case, lava was forced through the rent and burst out at the side of the mountain. In the other, the brilliant light which was emitted indicated the presence of molten lava deep down in the fissure. Now, when we combine these circumstances with the dike seen in the Val de Beauvais and with the similar appearances seen round the ancient crater of Vesuvius, we can come, as it appears to me, to but one conclusion. Before and during an eruption, the lava which is seeking for exit must be forced with such tremendous energy against the internal framework of the mountain's dome as to fracture and rend the crust, either in one or two enormous fissures or in a multitude of smaller ones. It does not follow that all or any of the fissures would be visible, because the outer surfaces of the crust may not be rent. Into the fissures thus formed the lava is forced by the pressure from below, and, there solidifying, the crust of the dome remains as strong after the liquid lava has sunk to its usual level as it was before the eruption. When we see dikes situated as in the Val de Beauvais, we learn that the fissures caused by the pressure of the lava extend far down the flanks of a volcanic mountain. That they are numerous is evidenced by the fact that those seen in the Val de Beauvais amount, according to Sir Charles Lyell, to thousands in number. And perhaps we may understand from such considerations as these the manner in which the Val de Beauvais itself was formed. For a wide strip of country between two great fissures might be so waved and shaken by the action of the sea of molten lava beneath as to be fractured crosswise, and then on the subsidence of the lava the whole mass below the fracture would sink down bodily. We gain an extended conception of the energy of the forces which are at work during volcanic eruptions, when we see that they thus have power to rend the whole framework of a mountain. Among recent eruptions of Mount Etna, one of the most singular was that of the year 1852, which began so suddenly that a party of Englishmen who were ascending the mountain and had nearly reached the foot of the highest cone were only able to escape with great difficulty. The eruption, which had commenced so abruptly, did not cease with corresponding rapidity, but continued with but few slight intermissions for fully 9 months. In the last week of May 1879, a fissure opened on the north side of the mountain, and volumes of smoke and flame were seen to issue from it. From the crater itself a great cloud of black ashes was poured forth, rendering the mountain invisible, said one writer, and obscuring the rays of the sun, by which the writer presumably meant obstructing their passage, even at a distance of many miles. These ashes were carried far and wide, and even covered the ground as far away as Reggio, on the adjacent coast of Calabria. 3 new craters opened in the direction of Randazzo, on the north side of the mountain, and the lava ran rapidly towards the town of Francavilla, where great alarm was felt, though that town is situated beyond the river Alcantara and on the very outskirts of the region usually threatened by eruptions. On the opposite side of the mountain, Palermo and the adjacent villa of Santa Maria di Licodia were also greatly alarmed. The new craters and the fissure with which the eruption began lay all on the northern side of the mountain. The stream of lava, which was estimated to be 70 meters, about 75 yards, in width, flowed in a direction somewhere between Francavilla and Randazzo, and reached the high road which encircles the mountain, and connects the latter town with the villages Linguaglossa and Piedimonte. These villages were enshrouded in a canopy of ashes, and almost total darkness prevailed in them. None of the ordinary concomitants of a great eruption were wanting. Balls of fire, or what were taken for such, were hurled into the air from the new craters and fissures, and, having reached a great height, they burst with a loud crash. Reports like the rolling of artillery were heard in the night, while night and day alike the stream of lava flowed stealthily and irresistibly on until it reached within a short distance of Linguaglossa. The terrible but magnificent eruption of the present year tends to confirm the belief of geologists that, if the Earth's internal fires are diminishing in intensity, the diminution takes place very slowly. A process of change may be going on which will result one day in the cessation of all subterranean movements, but the rate at which such a process is going on is so slow at present as to be imperceptible. We cannot point to a time within the historical era, or even within that far wider range of duration which is covered by geological records, at which the Earth's internal forces were decidedly superior in energy to those at present in action. Nor is this to be regarded as of evil import, but altogether the reverse. The work achieved by subterranean action, destructive though its immediate effects may often appear, is absolutely necessary to the welfare and happiness of the human race. It is to the reproductive energy of the Earth's internal forces that we are indebted for the existence of continents and islands on which warm-blooded animals can live. Had the primeval world been constructed as it now exists, says Sir John Herschel, time enough has elapsed, and force enough directed to that end has been in activity, to have long ago destroyed every vestige of land. So that, raising our thoughts from present interest to the future fortunes of the human race, we may agree with Sir Charles Lyell that the most promising evidence of the permanence of the present order of things consists in the fact that the energy of subterranean movements is always uniform, when considered with reference to the whole of the Earth's globe. End of Etna's Eruptions, Part 2. Knowledge, September 1886. Plant Invasion on Hawaiian Lava Flows by Professor F. Cavers. This LibriVox recording is in the public domain. The re-vegetation of Krakatau, which was deprived of vegetation by a series of volcanic eruptions in 1883, has been followed out by Trube, Ernst, and other observers. A detailed account is given in The New Flora of the Volcanic Island of Krakatau, Cambridge University Press, 1908. Successive lava flows from Mauna Loa in Hawaii, by far the largest volcano in the world, have afforded an opportunity for similar observations there, especially as the age of many of the flows is exactly known. Forbes, Occasional Papers of the Museum of Polynesian Ethnic and Natural History, Volume 5, has published a preliminary account of the plant invasion of some of these flows. The lava is of two well-defined kinds, called by the Hawaiians pahoehoe and a'a. The former has a smooth but billowy or hummocky surface and is marked by lines showing that it cooled as it flowed, while the a'a is lava broken into fragments having sharp and jagged edges, probably owing to subterranean moisture having made it cool from below upward instead of from above downward, as in the case of the pahoehoe. On 1859 flow, Forbes found no vascular plants on the a'a, though the surface was often white with lichens, while contrary to what might have been expected, the smooth pahoehoe was much more richly covered with vegetation, which, however, occurred only in cracks. On a 1907 flow, plants were found just beginning to be established. Evidently, on both types of lava, the first pioneers are low plants like algae and lichens. On the pahoehoe, these are soon succeeded by ferns and seed plants, but on the a'a, there is a long-enduring lichen stage. Ultimately, the natural forest of the region returns, except in places where man's influence causes the successful invasion of a naturalized flora. In this forest, a species of Metrosideros is the dominant tree at first, while an acacia is the dominating tree of the ultimate or climax forest. End of Plant Invasion on Hawaiian Lava Flows by Professor F. Cavers. Knowledge, 1914. The Recent Eruption of Taal Volcano in the Philippine Islands by Charles Davison. This LibriVox recording is in the public domain. In the island of Luzon, nearly 40 miles south of Manila, lies Lake Bombon. Near the center of this lake, from Volcano Island, there rises Taal Volcano, which by its eruption last January 30th caused so much damage to the surrounding villages. The crater walls vary in height. At no point are they lower than 492 feet. At the highest, they rise to 996 feet. When the United States government took over the Philippine Islands at the close of the last century, they acquired the services of a Jesuit priest, the Reverend M. Sendera Maso, who for many years had studied and published valuable reports on the earthquakes and volcanoes of that unstable group of islands. Being appointed an assistant director of the U.S. Weather Bureau, Father Sendera Maso has continued his useful work, one of the latest results of which is the investigation of the recent eruption of Taal Volcano. Of his interesting report on this eruption, a summary is given in the present note. During the night of January 27th to the 28th, the volcano issued the first warnings of the coming eruption. Instead of the usual clouds of white steam, great puffs of black smoke were emitted from the main crater, accompanied by rumbling sounds and tremors. On January 28th and 29th, explosions and earthquakes became more frequent and stronger, until at about 2:20 a.m. on January 30th, they culminated in a tremendous explosion, the sound of which is said to have been heard at a distance of 250 miles. A huge black cloud rose from the crater, lit up by flashes of lightning, vivid sparks, and bursting globes of fire. A heavy fall of boiling mud followed the explosion and destroyed all the vegetation and the flimsy houses on Volcano Island and along the western and northwestern shores of the lake to a distance of 10 miles from the crater, and caused the death of between 1,250 and 1,300 of their inhabitants. On the accompanying sketch map reproduced from Father Sendera Maso's report, the black dots indicate the towns and villages that were obliterated, and the small crosses, those that were damaged. After the eruption, there was a rush of air towards the volcano, which was noticeable for many miles around. Barometers registered a rapid fall of atmospheric pressure, which at Batangas, 17 miles from the volcano, amounted to about 1/12 of an inch, and at Manila, 39 miles, to 1/25 of an inch. The distribution of the volcanic mud was governed by the direction of the prevailing wind, which was from the southeast. On Volcano Island and the western and northwestern shores of the lake, the mud formed a layer from 2 to 3 feet in thickness. With increasing distance, its thickness gradually diminished, until beyond a distance of 15 miles only gray, gritty dust was deposited. The finer dust was, of course, carried still farther, and on the morning after the eruption some fell at Manila. On the southeastern shore of the lake no mud was to be seen, and only a little was deposited on the eastern and northeastern shores. After the great eruption of January 30th, no other outburst of any importance took place, and the earthquake shocks soon diminished both in frequency and strength until they practically ceased on February 7th. Along the shores of the lake, the damage was increased by the waves produced in the lake, which reached a height of 10 feet. Here and farther inland, some injury was caused by earthquakes, more by the continual shaking than by the actual strength of any shock, for none of them attained a destructive degree of intensity. At the Observatory of Manila, nearly 1,000 shocks were recorded between the evening of January 27th and February 7th, none of which in that city reached an intensity greater than the 4th degree of the Rossi-Forel scale of intensity. In other words, the strongest were capable of making doors, windows, fire irons, etc. rattle. They produced a trembling sensation like that felt on a station platform when an express train passes. Other shocks of the 3rd degree were just sufficiently strong to be felt by human beings. The great majority of the shocks were of the 2nd and 1st degrees of intensity. They were microseismic movements requiring rather delicate instruments for their detection. The following table, founded on that given in Father Cedero Masso's report, shows the number of shocks of each degree registered at Manila from 11:6 p.m. on January 27 to February 7th. Intensity shocks on the Rossi-Forel scale. January 27th, 2 3rd degree, 3 2nd degree, 21 1st degree. January 28th, 10 4th degree, 21 3rd degree, 31 2nd degree, 135 1st degree. January 29th, 9 4th degree, 9 3rd degree, 28 2nd degree, 67 1st degree. January 30th, 8 4th degree, 10 3rd degree, 16 2nd degree, 62 1st degree. January 31st, 16 4th degree, 16 3rd degree, 28 2nd degree, 139 1st degree. February 1st, 12 4th degree, 11 3rd degree, 18 2nd degree, 89 1st degree. February 2nd, 4 4th degree, 3 3rd degree, 9 2nd degree, 61 1st degree. February 3rd, no 4th degree, 2 3rd degree, 7 2nd degree, 46 1st degree. February 4th, 2 4th degree, 2 3rd degree, 3 2nd degree, 32 1st degree. February 5th, 1 4th degree, no 3rd degree, 3 2nd degree, 23 1st degree. February 6th, no 4th or 3rd degree, 1 2nd degree, 14 1st degree. February 7th, no 4th degree, 1 3rd degree, no 2nd degree, 11 1st degree. It will be noticed that the shocks were most frequent on the day following the beginning of the eruption and on that after the great explosion. As this occurred at 2:20 a.m. on January 30th, it is evident that the explosion caused a temporary relief of the internal strains, such as might well give rise to the old view according to which volcanic eruptions were the safety valves that shielded us from earthquakes. End of The Recent Eruption of Taal Volcano in the Philippine Islands by Charles Davison. Knowledge, 1911. A New Volcanic Island, the Third Bogoslav. This LibriVox recording is in the public domain. Some weeks after the Californian earthquake, officers and crew of the Fish Commission steamer Albatross, while on their way under Captain L.M. Garrett to investigate with Professor Charles H. Gilbert the fisheries of Japan, passed a group of islands known as the Bogoslavs, and to their astonishment perceived that a third island had been added to the other two. Professor Gilbert, in a personal letter concerning the first sight of the island on May 28th, writes, "When I saw the Bogoslavs in 1890, there were really two small islands about 1.5 miles apart, one of them steaming and the other cooled off. As will presently appear, all three of the islands were of volcanic origin, one having arisen more than a century, and the other 23 years ago. This has been the condition for a number of years, so the hot one had received the name of Fire Island, the cold one Castle Island. When they came in sight yesterday, we were astonished to find that Fire Island was no longer smoking, and that a very large third island had arisen halfway between the other two. It was made of jagged, rugged lava, and was giving off clouds of steam and smoke from any number of little craters scattered all over it. Around these craters, the rocks were all crusted with yellow sulfur. In a later letter, written from Yokohama, Dr. Gilbert said, "I wrote you a full account of Bogoslav, but the letter seems to have miscarried. Our discovery seems to have been corroborated later by some revenue cutter, but if the newspaper report agrees with their findings, very extensive changes took place in the interval between the two visits. When seen by us, the new cone, occupying much of the space between the two older ones, was somewhat higher than either, but was certainly far from 900 feet high. 300 feet would be an extreme figure. There was no evidence of a central crater. The steam and fumes were given off most abundantly from cracks and fumaroles on the slopes. About these were heavy incrustations of sulfur. We saw no indications of boiling water, nor did we believe that landing would be impossible. As we have said in parenthesis, all three of the Bogoslavs, which are about 120 miles south of the Pribilof Seal Islands, have risen from the sea, hot and steaming, in historic times. The Pribilof Islands, as Professor Starr Jordan remarks in an article on the Bogoslavs in the Popular Science Monthly, New York, had an origin similar to that of the Bogoslavs. That they are of volcanic origin, their composition leaves no room for doubt. Of the older Bogoslavs, one of which has for 20 years been known as New Bogoslav, Dr. Grove Gilbert, writing 7 years ago, and noting the rapid disintegration of the islands, predicted that in this century the name Bogoslav would attach only to a reef or shoal, were it not for the possibility of new eruptions. It may be noted as a curious example of scientific prescience that Dr. Gilbert went on to say, "The pulse of the volcano is so slow that we have noted only 2 beats in more than a century. But such sluggishness must not be taken as a symptom of death, or even decline, for volcanic organisms are characteristically spasmodic in their activity. Long before the sea has established its perfect sway, the arteries of the mountain may again be opened, and a new and larger island put forth to contest its supremacy." The pulse of the volcano has certainly quickened, and the floor of the Bering Sea in this region seems to be still unsettled, so that astonishing changes may be looked for at any time. The oldest Bogoslav, now called Castle Island, rose from the sea in 1796, and Kotzebue describes the first glimpse of it as seen by a trader named Krinkhoff, who had been forced to seek refuge from a storm in a neighboring island. The birth of the volcanic islet was accompanied by an earthquake which shook the island where the traders had taken refuge, and by an outburst of fire with thunderous explosions. The island was said to emit fire for months afterwards, and for 8 years afterwards the water round it was warm, and its ashes unbearably hot. The eruption in 1883, in which the second Bogoslav, called Fire Island, was born, had no witnesses, but in September of that year great volumes of steam and smoke, accompanied by showers of ashes, were thrown out from the summit and through fissures in the sides and base, the bright reflections from the heated interior being visible at night. At the time of this eruption, a severe earthquake was felt in the sea off Cape Mendocino, apparently in the line of the Portola Tomalis Rift of April 1906. The islands were visited in 1884 by the officers of the U.S. revenue cutter Corwin, and Lieutenant J.C. Cantwell and Surgeon H.W. Yemens made the ascent of New Bogoslav. Lieutenant Cantwell thus describes his experience in The Cruise of the Corwin. The sides of New Bogoslav rise with a gentle slope to the crater. The ascent at first appears easy, but a thin layer of ashes formed into a crust by the action of rain and moisture is not strong enough to sustain a man's weight. At every step my feet crushed through the outer covering, and I sank at first ankle-deep, and later on knee-deep, into a soft, almost impalpable dust, which arose in clouds and nearly suffocated me. As the summit was reached, the heat of the ashes became unbearable. On all sides of the cone there are openings through which steam escaped with more or less energy. 7 years after that, Doctors Miriam and Mendenhall of the Bering Sea Seal Commission found the newer island still smoking, steaming, and occasionally roaring like a giant steam escape. The older island had quite cooled and had become a sheer cliff or hill of cold ashes, and was and is the home of countless seabirds, as well as of a small herd of sea lions. Captain Cook in the 18th century had passed by the neighborhood of this island. This was 18 years, however, before it was born, and he named a pillar of ash or rock which he found there Ship Rock. Ship Rock fell in ruins 5 years after the birth of Fire Island. The question which naturally arises is whether the rise of the newest Bogoslov was directly connected with the Californian earthquake. The possibility, remarked Professor Starr Jordan and Mr. Archibald Clark in the article from which we have quoted, is heightened by the fact that the great earthquake rift, which extends through the coast range of California for a distance of 200 miles, follows a direction which, if produced northward to Bering Sea, would pass near the islands of Bogoslav. Again, this earthquake rift was largest, and its effects more violent, when it entered the sea in Mendocino County than at any other point throughout its course, the extent of the lateral movement along the crack increasing from about 2 feet in Monterey County to about 16.5 feet at Point Arena, where it finally enters the sea. In opposition to this view may be placed the improbability that an earthquake rift or fault would extend so far as from the center of California to Bering Sea, a distance of more than 2,000 miles, and through such depths of water as intervene between Point Arena and Bogoslav. It is also stated that the evidence of the seismograph, so far as understood, favors the idea that the great earthquake was confined to California, although its center of disturbance was clearly in the sea in a westerly direction from Cape Mendocino. It is evident also that the rise of the third Bogoslav was attended by little, if any, disturbance in the immediate vicinity. The advent of each of the other 2 islands was marked by earthquake shocks, the fall of volcanic ashes, and displays of fire observed and felt by the people of Iqneous on Unalaska Island. The people of this village in 1906 were unaware of the presence of the new island until the news was brought in by vessels touching at the harbor. On the whole, the weight of evidence at present seems to favor the idea that the Bogoslav disturbance of 1906 was local in character, and the coincidence in date with the California earthquake involves no actual relation between the 2 phenomena. End of A New Volcanic Island. Knowledge, 1907. Volcanic Carbon Dioxide by C. Ainsworth Mitchell. This LibriVox recording is in the public domain. The liberation of carbon dioxide from numerous vents is apparently the final manifestation of volcanic activity in the district of Auvergne. All the mineral springs in the neighborhood are heavily charged with the gas, and one of those at Mont, which issues in a large crevice, has long been known as the poisoned well. Animals that take refuge in the crevice or come to drink the water are rapidly asphyxiated by the gas, which is always accumulating there. The bodies of birds, rabbits, dogs, and sheep are frequently found in this crevice, and many children have lost their lives in the same way. Hitherto, this was the only spring of the kind known, but recently it was noticed that the vegetation to the northeast was discolored by stains, and these were found to be due to the plants being poisoned by carbon dioxide liberated at these points. Acting on the advice of M. Glangeau, the owner of the land subsequently discovered several places where the gas was being emitted from fissures in the rocks. 2 springs were also found in crevices several yards in depth, and these crevices were particularly interesting from the fact that they contained Roman pottery and the skeletons of oxen, sheep, horses, and a man, and at a lower depth the skeletons of a mammoth and a bison, Bos priscus. All of these had apparently been asphyxiated by the gas in the same way as the animals of today. Some years ago it was pointed out that thousands of liters of carbon dioxide were being lost daily in Auvergne, and that it would be profitable to collect and liquefy the gas. This, it was shown, could be done very cheaply, and the product would be much purer than the ordinary commercial liquid carbon dioxide, which might contain poisonous impurities, such as carbonic oxide, whereas the natural gas contained only carbon dioxide and nitrogen. Liquid carbon dioxide has been prepared for some time past in the volcanic districts of Eifel and Westphalia, and now a start has also been made at Mont. The actual amount of gas at present liberated is about 500,000 liters per day, but a much larger quantity could be collected by means of suitable borings. End of Volcanic Carbon Dioxide by C. Ainsworth Mitchell. Knowledge, 1906. Saturated and Unsaturated Igneous Rocks by G.W. Tyrrell. This LibriVox recording is in the public domain. Professor S.J. Shand points out and emphasizes a distinction in the behavior and occurrence of igneous rock minerals with respect to free silica. Geological Magazine, November 1913. About half of these are capable of forming in the presence of free silica, and are associated in igneous rocks with quartz and tridymite. The remaining rock-forming minerals do not appear along with quartz, save in certain exceptional cases. The former set are the more highly saturated, the latter the less highly saturated compounds of their respective metallic elements, and are said to be saturated or unsaturated respectively with regard to silica. The saturated minerals have taken up their full complement of silica, whereas the unsaturated have not. Familiar examples are orthoclase and albite amongst the saturated, and leucite and nepheline amongst the unsaturated group. Professor Shand makes a distinction between igneous rocks according as to whether they are composed of saturated or unsaturated minerals. The groups thus formed correspond largely with those now known as calcic and alkalic. The unsaturated or alkaline rocks have in general a much greater action on the rocks they invade than have the saturated rocks, since they are capable of entering into chemical combination with the silica of the invaded rock masses. As a consequence of the chemical activity of an undersaturated magma, a great variation, both chemical and mineralogical, would be expected in an undersaturated than in a saturated igneous complex. This deduction is confirmed by the well-known variable character of alkaline rocks. Professor Shand thinks that the distinction may prove of use in classification. It may perhaps be pointed out that it is recognized in the American quantitative classification by the ratio which determines the orders in that system. This ratio contrasts the amount of quartz or lenads, feldspathoids, with that of feldspars. The rocks falling in the orders determined by the quartz-feldspar ratio are the saturated types. Those falling in the orders determined by the lenad-feldspar ratio are the undersaturated types. End of Saturated and Unsaturated Igneous Rocks by G.W. Tyrrell. Knowledge, 1914. The Genesis of the Diamond by W.H.W. This LibriVox recording is in the public domain. The genesis of the diamond has always been a somewhat vexed question. As everyone knows, the South African diamonds occur in pipes or necks of volcanic rock known as blue ground or kimberlite. This is of three kinds, derived from lava, breccia, and tuff, respectively, all of which consist in the main of highly basic or ultra-basic minerals, now for the most part altered to serpentine, mingled with many xenoliths of the country rock, and also of such deep-seated rocks as eclogite and granite. The diamonds are found in the pipes in crystals of all sizes, from the great Cullinan, weighing 1 3/4 pounds, to fine diamond dust, and occur both in the blue ground and also in the eclogite xenoliths. The first theory put forward to account for their presence was that they had been produced by the recrystallization of the carbon contained in shales, through which the pipes had been driven. That theory has long been abandoned, and up till lately 3 different hypotheses were current. These were as follows. First, that the diamonds were all of deep-seated origin, and that the pipes had only been active for a very short time, the diamonds being broken by the violence of the explosion. This is supported by the occurrence of diamonds in the eclogite. Second, that they were original constituents of the kimberlite and crystallized in place from carbon contained in solution in that rock. And third, that they were entirely secondary minerals. In a paper in the Mining Journal for May 1916, Messrs. Draper and Goodchild put forward another theory, which is to some extent a combination and amplification of all the foregoing. First of all, they suggest that the kimberlite is a product of magmatic differentiation in the pipes at the close of the activity, when the lava had ceased to flow and was not yet cooled. They then point out that, though diamonds are found in the deep-seated eclogites, they are never of large size, as are those in the blue ground. In the blue ground itself, also, there are found many minute diamonds. Now, the diamond in these rocks is an accessory mineral in the same way as zircon and rutile, and accessory minerals are always in small crystals. Therefore, the occurrence of diamonds of small size is what might reasonably be expected. The inference, therefore, is that the large stones of economic value are not original constituents of either the eclogite or the blue ground. It has been shown that at a temperature of about 1300 degrees centigrade, diamonds are dissolved by molten kimberlite, showing resorbed forms similar to that of quartz in porphyries in the short space of 30 minutes. There was evidently a considerable amount of sulfitaric action in the pipes at the close of the volcanic period, and it may well be imagined that under the influence of fluxes, such as heated water, the smaller diamonds could be dissolved by the magma and redeposited as the large stones of commerce, the phenomenon being akin to that of secondary enrichment. There are some objections to this theory, the chief being the general absence of intense metamorphism, both of the rocks surrounding the pipes and of the included fragments. But it is a very interesting addition to our ideas on this knotty subject. End of The Genesis of the Diamond by W.H.W. Knowledge, 1916. Notes on Earthquakes by Richard A. Proctor. This LibriVox recording is in the public domain. The Earthquake of Calabria. No earthquake has ever happened, the circumstances attending which have been so carefully noted, as in the case of the earthquake of Calabria in 1783. This celebrated earthquake began in February 1783 and lasted until the end of 1786. The first shock threw down, quote, in 2 minutes nearly every house in all the cities, towns, and villages, from the western flanks of the Apennines in Calabria Ultra to Messina in Sicily, and convulsed the whole country, unquote. The second took place 7 weeks later and was scarcely less violent. Sir Charles Lyell mentions that the great granite chain which passes through Calabria from north to south and attains the height of many thousand feet was shaken but slightly by the first shock, but rudely by those which followed. The manner in which a large extent of country was permanently affected by this earthquake is very well worth noticing, as affording an excellent illustration of the mode in which earth waves travel. The Apennines are formed for the most part of massive and hard granite, with steep inclines, upon the base of which lie those strata of sand and clay which form the Calabrian plains. These plains are usually level, but are intersected in places by narrow valleys and ravines whose sides are almost vertical. The effect of the earthquake was to shake down those parts of the Calabrian plains which border on the granite backbone forming the Apennine range. The soil slid over the solid and inclined nucleus and descended somewhat lower, says Lyell, leaving almost uninterrupted from St. George to beyond St. Christina, a distance of from 9 to 10 miles, a chasm between the solid granite nucleus and the sandy soil. Many lands slipping thus were carried to a considerable distance from their former position, so as entirely to cover others, and disputes arose as to whom the property which had thus shifted its place should belong to. The whole of the country over which the effects of the great shocks extended was at times heaved simultaneously, like an angry sea, and sensations resembling seasickness were experienced by many of the inhabitants. Those who have watched the sky from the deck of a sea-tossed ship will have noticed that the drifting clouds seem at times to be arrested in their motion. It is in reality the ship which is moving for the moment in the same direction as the clouds, and thus neutralizes the effects of their motion. The same phenomenon was observed during the Calabrian earthquake, and nothing serves to give us a stronger impression of the turbulence of those internal heavings which make the dry land as unstable as the billows of a swelling sea. Trees whose roots continued firmly embedded in the soil were seen to lash the ground with their branches. It will be evident that the seat of disturbance was beneath the rocky ribs of the Apennines. The superincumbent soil was swayed with violence by the vibrating mountain slopes, but the chief mischief followed when the vibration ceased. For then the soil to which motion had been communicated began to slide over the now stationary granite, and this sliding motion being quickly checked by the irregularities of the rocky substratum, there resulted a destructive shock to all objects, houses, trees, or living creatures, upon the shaken plains. One may illustrate the nature of the shock as follows. Suppose a small tablecloth to be lying on a large table with raised edges, and that a variety of objects stand upon the cloth. Then, if the table be shaken with a gradually increasing violence, these objects may continue in safety, provided the motion is so managed that there is no abrupt change of direction, and no sudden increase or diminution of velocity. If the motion of the table be suddenly checked, the cloth would not immediately lose its motion, but would slide until it was stopped by the raised edge of the table, and objects on the cloth would move with it until its motion was checked, when they would receive a shock more likely to be destructive than any which had been communicated to them while the motion of the table continued. And just as such a cloth would rumple up as soon as the motion of one end was checked, so the soil of the Calabrian plains was found to be in some parts abnormally raised, in others as strangely depressed. In the town of Terra Nuova, says Sir Charles Lyell, some houses were seen uplifted above the common level, and others adjoining sunk down into the earth. In several streets the soil appeared thrust up, and abutted against the walls of houses. A large circular tower of solid masonry, part of which withstood the general destruction, was divided by a circular rent, and one side was upraised, and the foundations heaved out of the ground. As might be expected, the soil did not continue unbroken by the violent shocks to which it was subjected. In the central parts of the disturbed region, the earth opened so widely as to swallow up large houses. In Canamaria, many buildings were completely engulfed in one chasm, insomuch that not a trace of them was ever seen afterwards. So violently did these chasms close their yawning jaws, that afterwards, when excavations were made for the recovery of valuables, the workmen found the contents of houses crushed into a compact mass with detached portions of masonry. In some instances, persons were engulfed by one shock and thrown out again alive by the following one. The magnitude of some of the fissures which were formed during this earthquake affords startling indications of the tremendous violence of the earth's internal throes. Grimaldi observed in the territory of San Fili a newly formed ravine half a mile long and 25 feet deep, and another of similar dimensions in Rosarno. In the district of Plesano, 3 enormous fissures were formed, one 1/4 of a mile long, about 30 feet in width, and 225 feet deep. The second, 3/4 of a mile long, 150 feet broad, and 100 feet deep, and the third, nearly a mile long, 105 feet broad, and 30 feet deep. If any evidence were required as to the true nature of the disturbance, it would be found in the remarkable motions of masses slightly attached to the surface soil. Paving stones were flung into the air, and masses of loose soil flung in showers over the surrounding objects. In this earthquake, 40,000 persons are supposed to have perished, and about 20,000 by the epidemics which followed. Dolomieu gives a painful account of the appearance of the Calabrian cities. "When I passed over to Calabria," he writes, "and first beheld Polistena, the scene of horror almost deprived me of my faculties. My mind was filled with mingled horror and compassion. Nothing had escaped. All was leveled with the dust. Not a single house or piece of wall remained. On all sides were heaps of stone, so destitute of form that they afforded no idea of there having ever been a town on this spot. The stench of the dead bodies still arose from the ruins. I conversed with many persons who had been buried for 3, 4, or even 5 days. I questioned them respecting their sensations in so dreadful a situation, and they agreed that, of all the physical evils they endured, thirst was the most intolerable, and that their mental agony was increased by the idea that they were abandoned by their friends who might have rendered them assistance. The destruction of the Prince of Sayala and a great number of his vassals was one of the most remarkable events attending this deplorable catastrophe. He had persuaded his servants to seek their fishing boats for safety, and went with them to encourage them. During the night of February 5th, while they were sleeping, an enormous mass of earth was flung from Mount Jossi upon the plain near which the boats were moored. Immediately the sea rose more than 20 feet above the level of the plain. Every boat was sunk or dashed upon the beach, and hundreds of persons who had been sleeping on the plain were swept out to sea. The prince and 1,430 of his servants perished. Earthquake at Riobamba. One of the most remarkable earthquakes ever experienced was that which overthrew Riobamba on February 4, 1797. A district 120 miles long and 60 broad was shaken by an undulatory motion which lasted for 4 minutes, and a far wider district felt the effects of the disturbance. Within the space first named, in which the movement was more energetic, every town and village was leveled to the ground, and many places were buried under large masses flung down from the surrounding mountains. Among these was the flourishing town of Riobamba. Preceded and accompanied by no warning noises whatever, the terrific concussion in a few moments effected the complete desolation of the unhappy district. The earthquake was a singular combination of perpendicular, horizontal, and rotary vibrations. So violent was the perpendicular, or as it may be termed the explosive movement, that hundreds of the wretched inhabitants were flung upon the hill La Cula, several hundred feet high, on the further side of the small river Licon. Then came a horizontal movement, so rapidly succeeding the other that in many instances the furniture of one house was found beneath the ruins of another. In some cases, property was removed so far from its original place that disputes arose among the survivors of the catastrophe, and the audiencia, or court of justice, was for some time occupied in adjusting these difficulties. Not less remarkable were the effects of the circular or rotary concussions. Walls beyond the town were twisted round without being flung down. Rows of trees which had been parallel were deflected in the most remarkable manner, and the direction of the ridges of fields covered with various kinds of grain was observed to be altered by the effects of the earthquake. Humboldt, it may be mentioned, explains in a somewhat unnatural manner the peculiar effects we have spoken of above. He conceives that the fact of the furniture of one house being found under the ruins of another seems to show that the movement was first directed downwards, then horizontally, and then upwards. This appears to me wholly improbable. In the first place, it has been almost constantly observed that the upward motion, in earthquakes which exhibit perpendicular vibrations, precedes the downward. And secondly, had the downward motion taken place first, it seems most probable that neighboring houses would have sunk side by side, so that the following horizontal movement would only have resulted in the forms of destruction ordinarily observed in earthquakes. The more natural view seems to be that there was first a violent upward movement, flinging the less firmly built houses bodily upwards, and merely destroying others, then immediately followed by a downward movement and a horizontal one, bringing the latter class of houses beneath the falling ruins of the others. Or it may be that so violent was the first upward movement that the upper parts of all buildings were flung into the air, whence, not partaking in the horizontal movement which displaced the foundations and lower part of the houses over debris of the buildings that they had not belonged to originally. An upward, followed by a downward, and then by a horizontal movement might result in either form of demolition, or in both. A short time after the destruction of Riobamba, a fearful subterranean rumbling resembling the loudest thunder peals was heard under the cities of Quito and Ibarra, the former more than 100 miles from Riobamba. Earthquake noises. The subterranean noises heard during earthquakes are sometimes singularly striking. The nature of the noises is very various, says Humboldt, rolling, rattling, clanking like chains, occasionally like thunder close at hand, or it is clear and ringing, as if masses of obsidian or other vitrified matters were struck in caverns underground. These noises are not only heard much farther off than they could be if they were transmitted in the air, but they travel much more rapidly. In 1744, when the great eruption of Cotopaxi took place, subterranean noises were heard at Honda on the Rio Madalena. The crater of Cotopaxi, 17,000 feet above the level of Quito, is separated from it by the colossal mountain masses of Quito, Pasto, and Popayan, by innumerable valleys and precipices, and by an actual distance of no less than 500 geographical miles. The eruption which took place in the island of St. Vincent on April 30, 1812, produced subterranean noises resembling the loudest peals of thunder in Caracas, in the plains of Calabozo, and on the banks of the Rio Apure, a distance of upwards of 700 geographical miles. This, in respective distance, says Humboldt, was as if an eruption of Mount Vesuvius were to be heard in the north of France. But it is remarkable that subterranean rumblings and bellowings are sometimes heard when neither an earthquake nor the kindred phenomenon, a volcano, is in progress. Sonorous phenomena, Humboldt tells us, when accompanied by no perceptible shocks, leave a remarkably deep impression, even with those who have long dwelt in districts subject to repeated earthquakes. A singular instance occurred in the year 1784 in the highlands of Mexico. A sound was heard as of heavily rumbling thunder, alternating with sharp explosive bursts beneath the feet of the startled inhabitants of Guanajuato. The subterranean bellowings and thunderings, bramidos y truenos subterráneos, grew gradually more and more intense, and then decreased as gradually. Terrified by a phenomenon which seemed to forewarn them of an approaching and terrible catastrophe, the inhabitants fled from the town, leaving great piles of silver bars a prey to bands of robbers. But after a time the more courageous returned, and repossessed themselves of their treasure. For 1 month the subterranean grumblings were heard at intervals, though neither on the surface of the earth nor in the silver mines 500 yards beneath it was any movement of the earth perceptible. The earthquake as a restoring power. We are so in the habit of regarding the earthquake as an agent of destruction that it may sound paradoxical to assert that the phenomenon is surpassed by no other as a regenerative and restorative agent. Yet this is strictly the case. But for earthquakes, our continents would continually, however slowly, diminish in extent through the action of the sea waves upon their borders and of rain and rivers on their interior surfaces. Had the primeval world been constructed as it now exists, says Sir John Herschel, time enough has elapsed and force enough directed to that end has been in activity to have long ago destroyed every vestige of land. It is to the reproductive energy of the earth's internal forces that we are alone indebted for the very existence of dry land. To the same cause, undoubtedly, we owe that gradual process of change in the configuration of continents and oceans which has been for ages and still is in progress, a process the benefit derived from which cannot possibly be called in question. Our forests and our fields derive their nourishment from soils prepared for long ages beneath the waves of the ocean. Our stores of coal and of many other important minerals have been in like manner prepared for our use during the long intervals of their submergence. We build our houses, even, with materials, many of which owe their perfect adaptation to our wants, to the manner in which they have been slowly deposited on what was once the bed of ocean, and compressed to a due solidity and firmness of texture beneath its depths. If it is indeed true, as Humboldt asserts, that the destiny of man is in part dependent on the fashion of the outer crust of the globe, on the partitioning of continents, on the direction of the mountain chains which traverse them, and on the distribution of land and water, then we must look upon the earthquake as the most important of those agencies which tend to the renovation of our terrestrial globe. So far from dreading lest the earth's subterranean forces should acquire new energies, we ought rather to fear lest they should lose their force. We may therefore gladly hail the opinion of the great geologist who asserts that the energy of subterranean movements has always been uniform as regards the whole earth. The force of earthquakes, adds Lyell, may for a cycle of years have been invariably confined, as it is now, to large but determinate spaces. Gradually, however, this force shifts in position so that other regions, for ages at rest, become, in their turn, the grand theater of action. End of Notes on Earthquakes by Richard A. Proctor. Knowledge, February 1886. The Eruptions in the West Indies by C.D. This LibriVox recording is in the public domain. Soon after the great eruptions in Martinique and St. Vincent last May, the Royal Society appointed a small commission to investigate the phenomena in both islands, and especially in St. Vincent. Dr. Tempest Anderson, a well-known student and photographer of volcanoes, and Dr. John S. Flett of Her Majesty's Geological Survey left London on May 28th. They arrived at Barbados on June 8th and proceeded to St. Vincent, where nearly 4 weeks were spent, chiefly at Chateau Belair and Georgetown in the neighborhood of the Soufriere. Early in July, they visited Martinique for 6 days in order to ascertain the general points of difference and similarity between the outbursts of Mount Pelée and the Soufriere, the phenomena in this island being studied by a French scientific commission under the directorship of Professor Lacroix. On their return to England, a preliminary report was presented to the Royal Society and was printed immediately in the proceedings. As some time must elapse before the complete report is published, we give here a summary of this first paper, quoting fully from the interesting account of the eruption of Mount Pelée observed by the Commission on July 9th. The eruption of the Soufriere. The island of St. Vincent is oval in form, 18 miles long from north to south and 11 miles broad. The main axis is occupied by a mountain chain composed entirely of volcanic materials. In the south of the island, volcanic action has long been extinct or dormant, but at the north end stands the still active Soufriere. This mountain, which is 4,048 feet in height, is a simple cone like Vesuvius, without lateral or parasitic craters. Its principal crater, known as the Old Crater, is nearly circular in form. Before the recent eruption, it was 1/19 of a mile across and about 1,100 feet deep. The bottom was occupied by a lake, said to have been over 500 feet deep. On its northeast lip is a smaller crater, 1/3 of a mile in diameter, called the New Crater, as it is supposed to have originated in the eruption of 1812. The remains of a gigantic crater ring surround the cone on its north side, bearing the same relation to it that Somma does to Vesuvius. Deep valleys have been cut in the slopes of the mountain, especially on its southern side, and it is in these that the greater part of the ejecta of the recent eruption have collected. For more than a year before the eruption took place, the north part of the island was subject to frequent violent earthquakes, and as far back as February 1901, 2 settlements of the Aboriginal Caribs were considering the advisability of deserting the district. About midday on Tuesday, May 6th, the first signs of the eruption were observed by residents on the southwest side of the mountain. At 2:40, there was a considerable explosion, and a large cloud of steam ascended into the air. At 5 p.m., a red glare was visible in the steam cloud on the summit. At midnight, there was a great outburst, and red flames were noticed on the lip of the crater. Next morning, gigantic mushroom-shaped clouds could be seen rising to a height of about 30,000 feet, and drifting away before the northeast trade wind. As the day advanced, the eruption increased in violence. By 10:30 a.m., enormous clouds of vapor were being emitted with loud noises, accompanied by much lightning, and it could be seen that the materials were mostly, if not entirely, discharged from the old crater. The activity now became continuous. Huge columns of vapor ascended with frequent violent outbursts, projecting showers of stones and mud on all sides, and chiefly to the east. At midday on Wednesday, May 7th, the slopes of the mountain were still green, though a layer of fine ash, just sufficient to give the leaves a grayish color, had fallen over the lower ground. About this time, it was noticed that steam was rising from some of the valleys on the south side of the mountain. Soon afterwards, the rivers Wallabou and Rebecca on this side were seen rushing down in raging floods of boiling water, and the whole mountain became enveloped in a dense cloud of vapor. The crater lake seems to have been driven over the lower or south lip of the crater, and to have poured down the valleys as a tremendous rush of boiling water to the sea. It is remarkable that, so far, the inhabitants on the east or windward side of the island had not realized their danger. As is frequently the case, the summit on this side was wrapped in cloud. Even on the morning of Wednesday, May 7th, sugar-making was in progress on several estates. By midday, however, all were convinced that the noises heard continuously were not due to a thunderstorm. But it was then too late to escape. for the Rebecca and other streams, usually dry except after rains, were running boiling hot and could not be crossed. It was here that the loss of life was greatest, the number of persons killed being estimated roughly at 2,000, including about a dozen white men. On the opposite side of the island, the loss was comparatively small. The view of the crater was clear, and the early outbursts of steam gave ample warning to the inhabitants, who fled along the coast to Chateau Pelée and other places to the south. To return to the eruption. At 1 p.m., the roaring of the volcano was tremendous, and after the large outburst, which took place every few minutes, volumes of vapor might be seen covering the whole area. So far, there was nothing abnormal in the eruption, and the destruction was confined to the higher parts of the mountain. But about 2 p.m. there was a rumbling and a large black outburst with showers of stones. A strange black cloud, laden with hot dust, swept down the mountainside, burying the country in hot sand, suffocating and burning all living creatures in its path, and devouring the rich vegetation of the hill with one burning blast. On the west coast, most of the inhabitants had escaped, but a few persons overtaken by the black cloud were killed or badly burned. One boat was near Richmond at the time the blast swept down. The heat is described as fearful. Hot sand rained into the boat, and the sea around was hissing with its heat. The darkness was so intense that a man could not see his hand. On the east side of the island, a dense black cloud was seen rolling with terrific velocity down the mountainside towards the sea, flashing with lightning, especially when it touched the water. All survivors state that it was intensely hot and was charged with hot dust, and that it smelt strongly of sulfur. They felt as if something was compressing their throats, and as if there was no air to breathe. The suffocating cloud only lasted a few minutes, and by the time it had reached the coast, the sand it contained, though still at a very high temperature, did not set fire to wood or burn the clothes of those exposed to it. At some distance from the cloud, one observer describes it as a solid black wall of smoke falling into the sea about 2 or 3 miles from us. It looked like a promontory of solid land, but it rolled and tumbled and spread itself out until in a little time it extended quite 8 miles over the sea to the west. Then began the most gorgeous display of lightning one could conceive. It was still bright daylight, but the whole atmosphere quivered and thundered with wavy lines intersecting one another like trellis work. We were encircled in a ring of fiery bayonets. Intense darkness now covered the whole north of St. Vincent. The roaring of the mountain was terrible. Fine ash and sand rained down over the whole country, with occasional showers of large stones, some of which were so hot as to set fire to the trash roofs of huts 7 miles from the crater. The eruption, in all probability, had reassumed the ordinary phase, the showers of ash and stones being produced by violent upward explosions of steam. Shortly before nightfall, the darkness lessened slightly, but the rain of dust and the noises lasted till early on the following morning, May 8th. When day broke, the volcano was still emitting puffs of slaty-colored steam, and showers of fine dust were falling on the west side of the mountain. A week later, May 15th, the volcanic activity had apparently subsided, and the mountain remained clear and unclouded until Sunday, May 18th, when a second, but much slighter eruption took place. The noises were as loud as before, the lightning very vivid, and ashes and sand fell freely for some hours. Clouds of steam were sometimes seen gently rising for some days later, but no further outburst took place until after the publication of the preliminary report. When the English Commission arrived in St. Vincent on June 10th, the Soufriere and the surrounding country to the south of Chateau Pelée and Georgetown were still covered with a layer of ashes, mostly in the form of a fine sand, mixed with spongy bombs and many ejected blocks composed of fragments of the old rocks of the hill. The latter consist of weathered andesites and andesitic tuffs, such as can be seen in the walls of the crater, some of them being more than 5 feet across. The larger bombs are often black, highly lustrous, and glassy when broken across. Some seen at Wallabou, 4 miles from the crater, were 3 feet in diameter. The sand, when dry, is yellowish-gray in color, but when wet becomes almost black. It contains plagioclase feldspar, hypersthene, augite, magnetite, and fragments of glass, and represents a fairly well crystallized hypersthene andesite magma, which has been blown to powder by the expansion of occluded steam. Owing to the heavy tropical rains and the quick growth of vegetation, this deposit was rapidly disappearing. Around Georgetown, it was from 1 to 3 feet deep, in the Carib country 4 feet, while on the higher slopes of the hill, where it had gathered in hollows, it reached a depth of from 5 to over 12 feet. Those who visited the country shortly after the first eruption described it as having a smooth, gently rolling surface, like that of blown sand. It is clear that immense quantities of hot sand had rushed down the hill into the valleys in an avalanche which carried with it a terrific blast and piled the ashes deep in the sheltered ravines, at the same time sweeping everything off the exposed ridges which lay between. For some days after the eruption, the stream valleys were level with their banks. But on May 24th and 25th, nearly 8 inches of rain fell, and with this the rainy season set in. After a heavy tropical shower, valleys that were usually dry were occupied by a thundering torrent several feet deep and 20 or 30 feet across, that soon swept away the ashes from the upper part of their channels. But in the lower valleys, which had been filled with thick masses of hot sand, the process of removal was still, in the middle of June, going on, and a curious spectacle was seen after every shower. The streams, by undermining their banks, caused landslides, and when the hot ash fell into the water, columns of muddy water rose to about 200 feet, carrying with them pieces of stone, while immense clouds of steam shot up to heights of 700 or 800 feet, expanding in great globular masses, exactly like the steam explosions from a crater. When Doctors Anderson and Flett ascended the Soufriere, there was the clearest evidence of the passage of a hot blast laden with sand. Near the shore on the east side, the sugarcane fields were covered with 3 or 4 feet of sand and scoria. The trees were all bare, a few branches broken, but no trees were uprooted or thrown down. At this point, the velocity of the blast was not above that of an ordinary gale, and the dust it carried, though hot, was not incandescent. At an elevation of about 1,000 feet, a further stage of devastation was encountered. The fields were swept bare, the trees broken down, though not as a rule uprooted, their smaller branches swept away. A deep layer of black sand covered the crops of sugarcane. The blast was here a violent gale. A little further up, enormous trees, even great cotton trees, 10 feet or more in diameter, had been uprooted and cast down, the fallen trunks in every case pointing directly away from the crater. The smaller trees were sometimes swept away like straws. Most were charred, some deeply, but as the wood was green, only the smaller branches had been consumed. The effect was like that produced by a violent hurricane, only more complete, for many of these trees had withstood the hurricane that ruined St. Vincent in 1898. Still higher, or above the 1,500 feet level, there was little left of the rich tropical vegetation which had covered the mountain. Blackened remains of tree trunks were to be seen, overturned or broken off near the ground and buried in dark sand. The highest parts of the mountain formed as bare and desolate a scene as could be imagined. The ash was 5 to 12 feet deep, and contained a good deal of burnt timber, utterly blackened and converted into charcoal. Everything was mown down, and there was nothing to show what was the velocity of the blast when it left the crater. The structural modifications produced upon the mountain were very slight. No fissures were seen, no parasitic craters or cones were formed, and there were no lava streams. Even the craters at the summit retain essentially their old configuration, though the outline of the lip of the crater, as seen from Chateau Bel Air, has undergone some slight changes, and the southern edge is somewhat lower than it was before the eruption. The inner slopes of the crater, formerly richly wooded, are now naked slopes or precipices of rock. The depth of the crater was generally estimated at about 1,600 feet. The bottom, when seen by the English Commission, was nearly flat or slightly cup-shaped, and contained 3 small lakes of greenish and turbid water. The eruption of Mount Pelée. Mount Pelée, like the Soufriere, is a simple cone with a large vent near the summit and without parasitic craters. Both mountains are deeply scored with ravines, and on the southwest side of each there is a broad valley, occupied by St. Pierre in the one case and by the valley of the Walabou in the other. It is in these valleys that the destruction was most pronounced. In St. Vincent, however, the mass of material ejected and the area devastated were much greater than in Martinique. The loss of life was less, but this was due to the absence of a populous city at the foot of the Soufriere. On Mount Pelée, the blast that overwhelmed St. Pierre was emitted from a triangular fissure, which opened on the south side of the mountain. On the Soufriere, the blast came from the old orifices. The eruption in Martinique began with the flow of mud lavas, while none such were seen in St. Vincent. These are the chief points of difference between the two eruptions. On the other hand, both were characterized by a complete absence of lava streams and by the paroxysmal discharge of hot sand and dust mingled with a small proportion of bombs and ejected blocks. The hot blast which swept down on St. Pierre was similar to that emitted by the Soufriere. During their brief sojourn at Martinique, Messrs. Anderson and Flett were fortunate in witnessing one of the more important eruptions of Mount Pelée, evidently a counterpart of that which destroyed St. Pierre. On July 9th, they were near St. Pierre in a small sloop that had been hired for their expeditions. During the morning, the volcano was beautifully clear, and only occasional jets of steam rose from the triangular fissure that served as a crater. A little after midday, however, large steam clouds began to rise, one every 10 or 20 minutes, with a low rumble. While they rose, they expanded, and, as they consisted of many globular rolling masses, they bore some resemblance to a gigantic cauliflower. About 6:30, it was obvious that the activity of the mountain was increasing. The cauliflower clouds were no longer detached, but arose in such rapid succession that they were blended in a continuous emission. A thick cloud of steam streamed away before the wind, so laden with dust that all the leeward side of the hill and the sea for 6 miles from the shore were covered with a dense pall of fine falling ash. Just before darkness closed in, we noticed a cloud which had in it something peculiar hanging over the lip of the fissure. At first glance, it resembled the globular cauliflower masses of steam. It was, however, darker in color, and did not ascend in the air or float away, but retained its shape and slowly got larger and larger. After observing it for a short time, we concluded that it was traveling straight down the hill towards us, expanding somewhat as it came, but not rising in the air, only rolling over the surface of the ground. It seemed to take some time to reach the sea, several minutes at least, and as it rolled over the bay, we could see that through it there played innumerable lightnings. As the darkness deepened, a dull red reflection was seen in the trade-wind cloud which covered the mountain summit. This became brighter and brighter. Suddenly, the whole cloud was brightly illuminated. In an incredibly short space of time, a red-hot avalanche swept down to the sea. It was dull red, with a billowy surface, reminding one of a snow avalanche. In it there were larger stones, which stood out as streaks of bright red, tumbling down and emitting showers of sparks. In a few minutes it was over. Undoubtedly the velocity was terrific. Had any building stood in its path, they would have been utterly wiped out, and no living creature could have survived that blast. Hardly had its red light faded when a rounded black cloud began to shape itself against the starlit sky, exactly where the avalanche had been. The pale moonlight shining on it showed us that it was globular, with a bulging surface, covered with rounded, protuberant masses, which swelled and multiplied with a terrible energy. It rushed forward over the waters, directly towards us, boiling and changing its form every instant. In its face there sparkled innumerable lightnings. The cloud itself was black as night, dense and solid, and the flickering lightnings gave it an indescribably venomous appearance. It moved with great velocity, and as it approached it got larger and larger, but it retained its rounded form. It did not spread out laterally, neither did it rise into the air, but swept on over the sea in surging globular masses coruscating with lightnings. When about a mile from us, it was perceptibly slowing down. We then estimated that it was 2 miles broad and about 1 mile high. It began to change its form. Fresh protuberances ceased to shoot out, or grew but slowly. They were less globular, and the face of the cloud more nearly resembled a black curtain draped in folds. At the same time it became paler and more gray in color, and for a time the surface shimmered in the moonlight like a piece of silk. The particles of ash were now settling down, and the white steam freed from entangled dust was beginning to rise into the air. The cloud still traveled forward, but now was mostly steam, and rose from the surface of the sea, passing over our heads in a great tongue-shaped mass, which in a few minutes was directly above us. Then stones, some as large as a chestnut, began to fall on the boat. They were followed by small pellets, which rattled on the deck like a shower of peas. In a minute or two, fine gray ash, moist and clinging together in small globules, poured down upon us. After that, for some time, there was a rain of dry gray ashes. But the cloud had lost most of its solid matter, and as it shot forward over our heads, it left us in a stratum of clear, pure air. The most peculiar feature of these eruptions, write Drs. Anderson and Flett in concluding their report, is the avalanche of incandescent sand and the great black cloud which accompanies it. The preliminary stages of the eruption, which may occupy a few days or only a few hours, consist of outbursts of steam, fine dust, and stones, and the discharge of the crater lakes as torrents of water or of mud. In them there is nothing unusual, but as soon as the throat of the crater is thoroughly cleared and the climax of the eruption is reached, a mass of incandescent lava rises and wells over the lip of the crater in the form of an avalanche of red-hot dust. It is a lava blown to pieces by the expansion of the gases it contains. It rushes down the slopes of the hill, carrying with it a terrific blast, which mows down everything in its path. The mixture of dust and gas behaves in many ways like a fluid. The exact chemical composition of these gases remains unsettled. They apparently consist principally of steam and sulfurous acid. There are many reasons which render it unlikely that they contain much oxygen, and they do not support respiration. End of The Eruptions in the West Indies by C. D. Knowledge, December 1902.